Good afternoon, all of you. Welcome at this pre-ENBIS conference workshop delivered by Effex, more specifically by José Nunez, the Chief Scientific Officer of Effex. José holds a bachelor degree in civil engineering. He also holds a master degree in operations research. That means he's good at mathematics and optimization. And José has done a PhD on design of experiments in my research group at KU Leuven. After that, José spent some time at the University of Madison in Wisconsin, and he came back to Leuven to continue his work as a postdoc and to prepare the launch of a spin-off company of the university, Effex, to valorize some of the newest findings in design of experiments. And that's one of the things that José will talk about today. So with José, you're in good hands today. I hope you enjoy the workshop.
Thank you, Peter. So welcome, everybody. As Peter said, Effex is a new company. It's a newcomer in design of experiment software, barely 1 year old. So we started in June 2023. We already have a solution end-to-end, as you will see, and that incorporates assets that have been developed during my PhD, but also during the research of other people in the group of Peter. So ideally, for the workshop, you will have a computer as well, because you will be getting a trial license to the software, so you can try yourself as well, and yeah, that will come later. So I will be talking about design, analysis, and optimization, and specifically about OMARS designs, which is one of the assets. I did my PhD on those and developed them further during the postdoc, and they are accessible through the Effex software. This is what we are going to cover today. Sorry. So we have 4 parts. It is quite long, so we have 4 hours, so I plan to have 3 breaks. The breaks are the blank lines. So we will start with some introductory material to design of experiments. I was not sure about the level of expertise of everybody here, so I am going to give some general introduction to the field. And then we will end the first part by signing up to the platform and launching an optimal design calculation. Then we will cover OMARS designs, first the theory, and then we will use the software to find an OMARS design for solving a screening and optimization problem at the same time. And then after the break, we will jump to the modeling and optimization parts of the software, where I will cover some theory behind, so I will explain you how we do things there. And I actually send you an email to all of you before with this presentation, and you have a few data sets that we will be using as well. And we will end with small bit that is on the platform features of the software, because it is web-based, so we have some collaboration tools and some, the software is not sold individually, but to companies, because we don't limit the number of users, but we limit the usage. So it's a little bit a different approach. You will get to know a bit more about the software there. I want to do it interactive, so if you have any question at any moment, just please ask, because otherwise if you write them down and ask them at the end after 4 hours, it would be probably more difficult. Let's get started. So, design of experiments, the 5 phases. What makes a design of experiment flow successful? It has 5 phases. The first is the preparation. So in the preparation, all the stakeholders, that normally there are many involved in a design of experiments, they gather and they discuss together. So they have to decide what are the factors that they want to study, what are the quality attributes of the end product or process that they want to measure, how they want to measure it, what are their specifications as well, what is the goal, the overall goal, So there is where everything is discussed and decided. Once that is decided, then we move to the next step, second, which is setting up the experiment, which is deciding which factor values are we going to test, such that the number of runs or the size of the design is respected and we gain the maximum information. Then we conduct the experiment, and once we have the data, we move to model selection. I will develop these phases a little bit further in the next slides. In the model selection, the goal is to find a model that relates inputs and outputs as best as possible, so we can identify what matters and what not, and quantify, and we can also predict. Which prediction, the power for prediction of the models is the base for optimization, where we use the models to get our product or process within specifications at the highest probability of success. So we made a little bit of a story around, because design of experiments, is a very useful technique, but it's not used as it should, or that's the feeling we have, people that we do design of experiments, because there is a gap. There is a gap between the practitioners and the knowledge that you need to set an experiment. So we actually prepared this booklet that you can take in the breaks or whenever you want, which is Design of Experiments for Newbies, where we explain in very layman terms these 5 phases and why design of experiments is important. So feel free to grab a copy. So we did for each one of the phases, and this is the first one, we made an analogy with a profession. So the first is the preparation, where all stakeholders, they gather, and this is the detective. Why? Because you have to be like a detective. You have to ask questions. You have to really inquire how the experiment will be done to identify any source of variability. So, of course, you have to set the inputs. You have to consider if there is batch-to-batch variability in the raw materials, if there are constraints. Sometimes you cannot use high pressure, high temperature at the same time. So you have to make a lot of questions as if you were a detective, not to forget anything. If you will forget a lurking variable, for example, a variable that influences the process, but is not considered in the design, your analysis may fail. So, very important phase, where importantly you also set the goal of the experiment, which is related to the size. So how many runs I can afford, because that will give you how much information you can get from it. That is, of course, related to the model. The second is the lawyer. So the second is setting the experiment. Once you have all the information about the experiment circumstances, you have to mathematically to find the best assignment of values of the factor for each test, such that you gain the maximum information. So that is what is called the experimental plan. Once you set the experimental plan, and that is of course discussed with the stakeholders as well, that is like a contract. So that should be respected as well as possible. Right? That's why we call this phase the lawyer. Importantly, a protocol is typically also established that will tell you how to perform the experiment, how to do it in a systematic way, not to introduce bias from any of the elements involved in the experiment, which could be machines, could be people, or daylight. Right. The third is when you conduct the experiment, and this we have made this metaphor with the scientist. And why? Because wherever you are, wherever sector you work in, if you are going to perform a design of experiments, you have to do it with the same rigor as a scientist. So you have to follow the protocol and to avoid including bias. So one of the most common systematic errors is not setting all the factors to the values that they are described in the experimental design. So it is recommendable that more than one person will will look at them. So there should be control as much as possible to follow the contract that everybody has signed. So when you move after you move ahead, so the experimental data is already available, and now you want to replace the experimental data with a mathematical model. So this is the explorer, because actually finding a meaningful model is like exploring. It's like exploring a new nature and finding either the path to reach a legendary lake with shores full of gold, which is the story that is written here in the booklet, or any other. So yeah, the metaphor that we use is that clearing the path towards the lake is like selecting a statistical model. So normally there, the model selection is one of the challenges in the whole data analytics field, how to choose the best effects that they will influence your quality attributes. Now, once you have a statistical model, a good statistical model could identify what matters, what not, and will quantify that importance as well. But it has another property which is very important, that is the capacity to predict. So once you give the model, you input some factor values, it will predict the quality attributes with a certain degree of uncertainty. So this is only one direction, yeah?
Normally, when you do a DOE, you suppose the model in advance without having the parameters, of course, but then you presuppose the kind of model that would be behind. And what if you're wrong in the model that you presuppose?
Yeah, then you run an insufficient experiment, of course. If your model is more complex, which will be the scenario, if there are like 3 factor interactions that are active cubic terms or quartic terms, you should be able to detect or to have some clues from the modeling stage and then come back to the design and augment the design and fit the model. Yeah, you are right that what you decide in the first phase in the preparation is like the maximum model you want to be able to estimate. And the model selection challenge consists of selecting which effects from that maximum model should go into the final model. Now, I was saying that one of the qualities is the prediction. So using a statistical model, you can predict, you can get the quality attributes once you input some factor values. But the one other property of the models is not only that direction, but the other one, which is the base for optimization. So optimization, we identify that as a magician because it uses the property of the models that they can predict, but on the other direction. So you can set the quality attributes that you want for your product or process, and then using the model, you can come back and identify what is the region in the factor space where all my quality attributes will be within specs. So this is a concept very used in pharma, which is called the design space, which is the region. Normally it's like a hyper-rectangular region where all the quality attributes will be within specs at the highest probability of success. So this is, of course, what the end goal in many experiments is, the optimization of the process. So recapitulation, I think is easy. Preparation, setting up the experiment, conducting the experiment, model selection, and optimization. And this is how we have also architecture the software. So we follow these steps. Right now, you are going to see solutions for the step 2, setting up the experiment, the model selection, and optimization. So a motivating example from the pharma industry is based on a real case, but with fake data. And we will cover the 5 steps again with this example. So it's a granulation challenge in the pharma industry. Once you identify the API, the active pharmaceutical ingredient, you need to put that into a tablet. And of course, not everything in the tablet is API, but it is filled with excipients, and the tablet is made in a certain way with certain machines that they have some configurations that they can change. So the granulation is essential to have a good production scale tablet press, and the granulation is influenced by several parameters. The experiment is very expensive because normally this is done at early stages of development where the API is very expensive, and of course the time is gold in pharma industries. So minimization of tests is very important. So we have input factors, critical quality attributes that characterize the granulation, and the experiment is limited to 27 tests because of the extreme cost of it. The stakeholders at the pharma company, they have gathered and they have discussed, and they have decided that these are the 8 factors that matter. So not only that, they specify how they are going to measure it, and they specify importantly the range for the quantitative factors. So they identify what is the factor space that they want to study, what is the minimum and the maximum value for the quantitative, and here there is a categorical one that has 2 levels. So this is crucial to identify well the ranges of the quantitative factors, not to be too narrow so that you don't gain any new information of the process, and not to be too wide so you get too many phenomena happening there that make modeling difficult. In the preparation phase, they also identify the quality attributes. So how are they going to measure the quality of a granulation process? What they are looking at? They were looking at 6 different quality attributes at the same time, which you see in the table. So the size distribution of the granule, packing ability, flow rate, and so on. They, of course, also specify how they are going to measure it, and they set the specs. So they also set what an ideal product will be. So you see that for the granule size, it should be minimized, less than 3, with target value of 1.5, and this happens with all of them. So this is one of the challenges of optimization, where you have multiple quality attributes, or responses as they are called in DOE, and they have to be optimized at the same time. So very often there are trade-offs between them that you have to take into account. Some of them, they may be more important than others. So this is, of course, another point in the process, the optimization, where every stakeholder usually has a say. Step 2. So we have defined what we want, and we set the experiment. This is an experiment. It's actually an OMARS design. So that was used in this example. Well, it was used in the real case, but of course the factors and the data is fake here. But you see here the color map on correlations of the chosen design. So this quantifies the absolute value of the correlation between the model matrix, so the different linear two-factor interactions and quadratic effects. And you see the property of OMARS designs that consists on this orthogonality, which means that main effects are orthogonal to each other and to all second-order effects. So this design has 24 runs, which is not sufficient to fit the full model. So the full model for 8 factors with 8 main effects, 28 two-factor interactions, and 7 quadratic effects, because we have 1 categorical. But it has very good properties, so it allows screening and optimization at the same time, and saves 3 tests for confirmation tests. Then the experiment is conducted at client facilities, so they do it with the same rigor as an expert, and they add this part to the table. So the quality attributes or the responses. So this is, yeah?
Yeah, on the previous slide you said, well, the full model is way too complicated for my 24 runs, but at the same time all the two second degree the interaction terms with each other have only moderate correlation. So we basically to understand both these things, but somehow I would think that, well, because the correlations are not perfect, it probably can estimate everything, but of course you can't. So.
Yeah, of course you can't because you don't have enough degrees of freedom to estimate all the effects at the same time. But these kind of designs, and we will see that in the next block, they have a property that is the projection property that it's quite good in these designs, and it consists of the fact that with these designs you can fit a large variety of models.
But then if you don't have enough tests to estimate all the parameters, then you have to choose which parameters you want.
Yes, challenge of the model selection.
Yes. So here you made some choices to remove some interactions and some productive effects.
Yes, I mean you will see in the how we solve it at the Effex. So we solve it in a, I think, a smart way. This is a huge problem, but it's also a huge problem in optimization experiments where you can fit the full model, because you don't want terms that they don't have any meaning there, right? So yeah, you're right. This is a challenge because you have to make a selection. But normally it has been shown that not every single factor is active, not every single two-factor interaction is active. And in that scenario is where these screening/optimization experiments, they shine. So we were here with the full data set after conducting the experiment, where we have one column per each response, all quantitative responses now. And then we go to the modeling challenge, the fourth step, which is of course very difficult because in this case, yeah, what I told you, we have 7 quantitative factors and 1 two-level categorical factors. So we have 43 different terms that they could go into the model. So 8 main effects, so many interactions and quadratics and so. So if you would like to consider all possible models, it will be, yeah, an absurd number that you cannot really cope, right? So this is the difficulty of modeling, and it happens for these problems, as you will see afterwards, that sometimes two models, statistically speaking, they are equally good. So this is also not easy to select. So this is the challenge of modeling, how to select the effects that they matter the most and not get unimportant effects in there. Sometimes if you will have a screening experiment, for example, which is an experimental design with a large number of factors and a reduced number of tests, you may have a screening goal, which is identifying the factors that they matter to do like next experiment, optimization experiment. So there it is very crucial that you identify what matters in your experiment. So this is the modeling challenge. And this is, yeah, I wanted to give some hints of how we solve it with Effex. Yeah, with the goal of repeating the information a few times so it will stay more, right? I see it every day, so for me it's not very new, but this is what you're going to see in the software, in the modeling part. What we have an all subset selection method that was actually developed in-house by Alan, this last person that is there. It is using optimization techniques, integer programming techniques, and it does succeed in looping through all these models, but it does it in a smart way. And it outputs the best models, so not a single one, which is what you get with forward selection or other model selection techniques, but it gets you the best models that they minimize the MSE for a specific number of terms. I will develop it further, but just takeaway is that in our software, we don't give you one model, but we give you a set of best models. And we represent it in a heat map, as you see here, where every column is one effect. So we have the main effects, interactions, quadratics, and every row is one model. And there you see in the best models that some effects, they come more often. Some quadratic effects are identified, and we also have a recommender system that will help you in finding the model. So this is model selection, and then we have optimization. Optimization is the cherry on top of the cake. It's what you want to do in the end. You want better process, better product, with better quality attributes, and this is, as you see, these are also screenshots of the software. You should set the specifications, which is what we have seen before. So these are the goals of the experiment here. So where we want every single response to be. And you can do it easily with this menu, where you set it to minimization on target, on interval, or maximization. And then we have several tools to explore this multi-dimensional space. So the solution that we developed focused on problems with many factors, many responses, multi-response optimization problems. You will see I give you already a hint. So again, with the same aim of repeating information, so it kind of stays more. This is a graph that we have where you see a discretization of the factor space. So the factor space is this first part, where we have the 8 factors and we make a discretization. So we have, this graph can handle hundreds of thousands of points. For each one, we calculate the predicted outcomes and we color it with the probability of success of being within the specs. And that allows this interactive multi-response optimization, where you can also explore yourself, make some. You will see it has different capabilities, but you can filter, and then you can explore and find the design space. Well, you see it here. So here I found it just for a very easy problem, of course, but you see this is a discretization of the factor space where the values are not the original, so I have been playing, just looking for the region that optimizes all responses, but you see that everything is yellow here, so any factor value combination within this, they will output a process or product that is compliant. Do you understand the graph? Are there any questions? I assume, yeah.
What's on the axis?
Yeah, okay. Every axis is, this is called a parallel coordinate plot. Every axis is one factor here. So we have the excipient 1, excipient 2, excipient 3, mass in time, spray rate, impeller speed, and so on. Here you have the range that this excipient 1 goes from 20 to 30, and it has been discretized in 5 different, in 4 segments, so 5 points, where you have the lower bound, then the center, and one in the middle, and then the upper bound, and one in the middle as well. And this has been done for every single effect. Here you have the categorical one that, of course, it has only 2 values. So discretization doesn't work on it. A line that goes from left to right, like this, like a piecewise line, is a specific combination of factor values. So it's a specific realization set of operating conditions. So a line from left to right means, okay, this is set to 20, this is set to 13, this is set to 12, this is, and so on. And for each of these lines, we calculate the predicted responses. So, and we color it with the probability of success of being within specifications. So there are a lot of lines here. So 5 to the power of 7 times 2. and they allow you to explore this multidimensional space. Any, yeah.
So it means that all the combination of the test that you mentioned at the left part of the graph gives you something within the design space.
Mm-hmm. Yeah.
Is in fact the design space.
Yes. Mm-hmm.
Can you see the actual KPIs as well, the measured responses on top of this? In some way?
What do you mean?
So the yellow band is the design space, but you've actually observed some responses, right? You measured some of those and
The real
Yeah.
data.
yeah, to see maybe you have some combinations that were in the design space and you
Ah.
want to see them maybe.
Right now we only work with the models. We don't have any input of the real data, but it's certainly a good idea. Yeah, thanks.
Yeah, so the color scale is the probability that the response variable is okay.
Mm-hmm. Yes.
Is there some spread or regime?
Yeah, I will have some slides specifically for that.
Yeah.
I had the same remark. It's amazing that you go so quickly from 1 to out of spec. I mean, there's hardly any red or blue or whatever color that is. It's going from yellow to immediately out of spec.
Yeah, because I have searched. If you see here, the ranges for the factors are not the original ones. For some of them, so it's not the full range of factors that you see here. So this, for example, goes from 7.5 to 13, right? The excipient 3. And if you come back to the specifications, excipient 3 goes from 5 to 15. So I have narrowed the factor space.
Okay, maybe I missed it. So the yellow part on the right side is the probability to be in spec.
Yes.
So and it's almost within that space there. It is almost everywhere 1. It's not that you have, let's say, areas that are where it gets risky.
No, that you have here, for example.
Yes, that's what I would expect.
Yeah, but once you start playing with it, and you say, okay, I am not going to consider the full range for this factor,
Okay.
but only an interval.
Okay.
And this is what you see here. So
Yeah.
It's a way to look, like a small lantern on the high dimensional obscurity.
And I guess you are not able to see which combination of factors give you which response in this graph. You see that all the combination of these factors give you something that is within spec, but you don't see.
We have an accompanying table you will see in the software that gives you the best points according to the probability of success, which is the last axis here. Mm-hmm.
Well, I'm wondering, would you do this based on one model that you select, or do you still keep the 20 best models or something, average over?
So far we do it with one model now. Yeah, model averaging is something we have in mind, for example. Yeah. Mm-hmm.
Can you elaborate a little bit on the model? I mean, you have 24 experimental units, so you're not going to estimate more than 24 parameters, that's for sure. So,
Yeah.
Can you elaborate a little bit? How many mean, because you say quadratic, you mean real quadratics, or you mean interaction terms?
No, real quadratics as well.
Real
Yeah.
quadratics.
Yeah.
Can you elaborate a little bit on the details of that model? How
Yeah.
many main effects, how many quadratics, how many interactions?
You can
Not
see.
too many, I mean, 23 will do.
Yeah, you can see the details of the model in the software that you choose, because in step 4, this modeling part, you finish this part by choosing a model, right? And then you can see what are the effects that are in the model, and you can see it there.
There's possibly an infinite number of parameter combinations that will fit just the
Yes, exactly. That's why modeling is so challenging for this kind of designs. Mm-hmm.
And when you say that it's based on the model, do you mean the point estimate of that model, or also does it also incorporate any uncertainty that you have on the estimate of the model parameters? To calculate
Good
the
question.
probability?
So we have different intervals. Of course, you will see when I describe the probability of success that not always is exactly a probability of success. So we work first with the confidence interval, then with the prediction interval, and then with the tolerance interval that takes that into account. Yeah. So you will see we assume as well at this point that all responses are uncorrelated. And yeah, coming back to your question, Eddie, in a practical case, I have seen that for this kind of designs, there was, I did a modeling with the Effex software, and the people at the company did another model. So we were fine. I mean, we found the same main effects also because it was an OMARS, but we differ in the second order effects. So they had a different second order effects than we had. But the best point, the prediction was the same. So the best optimal point, the optimal combination was the same.
But basically you don't care about the parameter estimates.
Well, like in mixers, right?
You only look at prediction.
You only look at prediction, yeah. If your goal is optimization, yes.
I was also wondering about this probability property, but I think you will elaborate more on it later.
I will, yeah. I
I was just wondering how you got to it.
I have an example on how it's calculated and.
Yeah, okay, I'll follow later.
Okay. Okay, Alan.
So just one general question. So maybe I missed that, but is it like from a real example? Like the data that you're showing is a real experiment?
The experiment was real, it happened.
And the responses?
The responses, I simulated them.
Okay, yeah, because that's why I saw a lot of decimals like next to
Yeah, exactly. Yeah.
So then in that example, out of curiosity, so because here you're showing several steps to solve a problem.
Uh-huh.
So in terms of, let's say, money, how much money did this company make by following these steps?
Well, this
by
is-
using Effex software. So what was like the change from what they were doing, and then thanks to Effex, they now reach, I don't know, higher levels of.
Well, that's a very good question, and I should have added that to the slides. So, thank you. So, at the NCS conference, because I think I can say it because it will be presented there, which is not this week, next week in Germany. So, some person from Sanofi will present this case, and they save more than 40% of their runs. So, they save several months of time. With using this, because before, actually the factors are not these factors either. You know, the factors I made them up as well, but they were doing two different experiments, and one for formulation, one for process. And because they could use the OMARS design, they could do everything at once, so they save substantial amount. And yeah, that's why they are using the software. And we have a talk there, so if you are coming there. Yeah, Eddie raised his hand
Do you
before.
calculate any aliases effects? So many of those parameter estimates are 100% confounded. So do you calculate which one are confounded and which one are pure? Well, there will not be too many pure estimates.
Yeah, it's not really needed, because the algorithm for model selection itself will not select two confounded effects, because they will not add to the objective function that it has. So that is kind of implicit in the modeling technique. I can send you the paper of Alan.
Does the software help you experiment in phases? For example, you do this, and then you think, oh, I'd like to learn a little bit more, and maybe collect some more data. Does the software help you with that?
At this point, that's you mean like design augmentation, right? For example, or
sorry,
design augmentation or
augmentation, for example. Yeah. So say you think, oh, I'd like to narrow my space a bit more, or I'd like to learn a little bit more about certain factors.
But I want to use the information that I had before.
I want to build on what I have.
Yeah. Right now, with the software, the proposal will be to focus on a narrow set of factors and fix other ones, maybe as a result of the optimization, and then make a design from scratch for those factors. Design augmentation is it's in the pipeline.
Right.
Yeah.
Thanks.
But we do have optimal design for the AI optimality, coordinate exchange algorithm, which is quite flexible, and it is plans to add. Okay. So now the third part, before we sign up into the software and we have a small demo and a break. How to assess the quality of a design, of an experimental design. Because in our platform you will see that even if you use the optimal design algorithm or the catalog, because you have two options to get an experimental design from our platform, is either you search the catalog and you get an OMARS design, or for other kind of problems you go to optimal design and then you get optimal designs for your problem. We don't give you a single design, so if you ask for an optimal design, the optimal for a given number of runs, we just don't give you that, because you can ask for, okay, give me the AI optimal designs for this number of factors and quantitative categorical, and for this range of number of runs. Then you get not one design, but several, because our platform allows comparing different designs with each other. It's one of the bases. It is something that we have seen in practice, that other software gives you a single design and it's kind of take it or leave it. The possibilities to compare designs with each other and make a more informed decision are somehow limited, so we provide that platform to compare them with each other. And that's why it's very important to know, or to have an agreement on how to measure the quality of a design. There are different, often conflicting goals when you measure the quality of a design. The first is maximize the quality of estimation, and this is very important for screening, where you want to identify the active factors to do a follow-up test, for example. So you really want to know that the estimates that you are getting are close to reality, and that's why normally you have several measures that they will minimize the variance of those estimates in one or other way. And this is, of course, the power to detect them, but also the D and A optimality, that they minimize this variance of the estimate, so once you get the estimate, you know that if it has a small variance, you are more sure the power is bigger, and so on. It's typical in screening experiments, where you have a large number of factors and a limited number of tests. Second is the quality of prediction, if you want to maximize that. That's when, for example, you don't care so much about being completely truthful to the model, but you want to predict well. Scenario for mixtures, for example, right? I mean, normally things are so correlated in the mixture space that you are interested in prediction mainly. And how you measure it? Well, normally you measure the prediction variance. So the models, they will give you a prediction variance that depends on which point of the factor space you are, and then you minimize either the maximum of it or the average through all the design space, and that is what the G and the I efficiency do. And of course you want also to minimize the correlation between the model matrix columns, so you don't get too much collinearity going on. And this is typical in optimization experiments, where you want to identify the design space, so this region where everything works. And now, the combination of estimation and prediction, which is something that we are going to look at, screening and optimization with a single design. Besides the properties that we have seen for estimation and prediction, we add another one, which is this projection properties of a design. So there is this word projection estimation capacity, which comes from literature as well. And here I give an example. So what does this number means? So the projection estimation capacity for a model with main and second order effects, well, model thesis, is denoted as this. P is C for a main effects and second order effects. And this is a single number. In this case, it equals to 3 for a 6-factor design, let's say. So this is a number that you can see in our software. What does it mean? Well, it means that with this experimental design, you can fit a full second order effects model on any subset of 3 factors. So you take any of the 20 subsets of 3 factors out of the 6, and then you build the model matrix with intercepts, main effects, interactions, and quadratic, and that model matrix will be full rank. This is one of the selling points, or it was one of the selling points, or it is, of the definitive screening designs, which made them say that definitive screening designs were designs for screening and optimization at once. So this is the basis. And this projection estimation capacity was equal to 3 for definitive screening designs. In OMARS designs, you can find 4, 5, and higher. Any question here? You will see that in the software, sometimes this value has a fractional value. So this measure has a fractional value. It may be 3.65. And that means that with that specific experimental design, you can fit a second order effects model on any subset of 3 factors and 65% of the subsets in 4 factors.
So that is just based on the assumption that all factors are important for optimization, because you 6 choose 3.
Mm-hmm.
So what do you assume here? Not all factors are important?
Yes, you assume effect sparsity. So you assume that in the final model, not every factor will be active for every second order interaction. And that's why these projection properties, they become important. Mm-hmm.
How do you calculate
That you take the design, you make all the 20 subsets of 3 factors, you build the model matrix for a second order effects model, you check if it is full rank, and if it is full rank, you calculate a bunch of quality indicators.
Does that mean that you could specify, say, I want pack meso 3, or I want a 4, and then with 4 you would need more runs to do the 4?
Yeah, exactly.
Right, okay.
In the catalog.
Yeah.
Not in the optimal design,
right.
But in the catalog, because catalog has 500,000 designs right now. They have been selected from a subset of 300 million designs. And yeah, we're keeping adding designs, like best designs to it.
If you happen to have one, it will show you that there is...
And we calculate it beforehand, yeah.
Right.
Because these calculations take time to...
And is there a straightforward way to go from 3 to 4? So suppose you say, okay, I'd like to do 3, so it will give me, I don't know, 30 runs or something, and then I say, oh, look at the results, and I think, oh, I need 4.
Yeah, you can filter it. You will see
Then
it's...
you have to add some, and can you then sort of say, well, how do I go from the 3 that I have to the 4 that I need?
You are still with extension.
Yeah, that's probably very hard, right? Or then you have to have some clever way of then saying, oh, I actually need 4, and I only budgeted for 3.
Yes, that's. I mean, that's kind of a research topic, because you could study the designs that we have and see if you can divide them, right, in 2 parts, for example. Sometimes some OMARS designs that we have are concatenation of 2 OMARS designs. So in that sense, yeah, that's a good point. Okay, fun, sign up. So you can take your computer. If you are not connected to the internet, the Wi-Fi and the password is just there. It's very easy. So Wi-Fi is Irish College and password is Irish College, all small letters.
Jose, since the software can be accessed from the cloud on any browser, is there any recommendation on whether to use a computer, or can I use my iPad, or can I use my cell phone to work on that?
The software is designed to be used from a laptop or a computer. It is a bit too complex to make it.
But then if I access from my iPad or phone,
I mean, you can.
see anything, or
You can, for sure. We don't guarantee a good UI experience, yes.
Yes. Do we sign up with the
Yeah,
create account?
yeah, I think you have a list of fields that you have to fill. We won't be sending you too many emails, promise.
All lowercase, all together.
We have to involve.
Ah, yeah, I didn't. So after filling in the form, you will be getting an email with a temporary password, so you have to log in with that email and change the password.
so perhaps I just want to make one comment to the audience, and I don't know if you have experienced it, but when I teach at the university, sometimes I'm using software and the students don't have the same equipment, so the equipment is like old or outdated, so I like the fact that we can access this through the web browser without installing anything. Because nowadays, something that I did in my course was to install RStudio in R. And if you try to do that during class, well, I encounter a lot of issues now. So nowadays, I think R and RStudio are quite complex to install in a classroom for students who are probably not experts. So the fact that we're using a web browser, I think is very attractive.
Nice. Yeah, thank you. I think, yeah, you're right. And that's probably why Shiny applications, they are quite popular now, right?
For how long do we have access to?
I think it's 4 weeks. 4 weeks,
4 weeks.
I think. guess everybody saw this, right?
So what are the terms and conditions for the license? Can we use it for academic purposes, commercial purposes?
Good question. They will come in a moment. So. So you should see something like this. Was it good? Yeah.
Something wrong with my laptop. I can't connect to the internet. I'm looking at this.
Okay. So to end this first part, we will do an optimal design calculation. But before, I want to tell you something about how we do optimal design in the software. So if I can have your attention. So what is optimal design? Optimal design is a very flexible approach that generates designs, experimental designs that are optimal according to a specific criterion, like DAI, for a specific model and specific number of factors and so on. So current software gives you a single optimal design for a given number of runs and a criterion. And every design is calculated from scratch. Right? It depends on the software. Some softwares, they have point exchange algorithms, so they have like a candidate set of design points and then they select them in the best way. Some other designs, softwares, they have coordinate exchange algorithm, which is a more advanced algorithm that changes every coordinate of the factor and loops until it is the best you can get. And this algorithm, the coordinate exchange, is what is implemented in Effex. But there are also different things. So we do things differently. We can calculate, as I said, optimal designs for different criteria and number of runs at the same time, and you can compare them. You can compare up to 50 different designs. So you can make a more informed decision. And this is an important one, we find. So we save the best designs that anyone has obtained for a given number of runs, a given criterion, and given number of factors, quantitative and categorical. We save the best always in a database. So every time you calculate an optimal design, we check in the database if there is a design that is better than yours.
Is this within one company or is this across companies?
This is across companies. It's a single database. So you are for sure that the design you are going to get, it won't be worse of any design that anyone ever got from the software, because we keep updating the catalog. Mm-hmm.
How do you evaluate the best design?
Optimal design, normally you do it for a single criterion, so you have a value for that criterion numerical, and then we obtain the optimal design from the coordinate exchange algorithm, so from scratch, when you click. Then we take the optimality value, we compare it to the designs that we have in the catalog for that same number of runs and same factors and so on. And then if the design is better, then we characterize it and we give it back to you. If the design is worse, we take the one from the database, which is faster as well. Yeah, so then we can come back. So there are several options in the software. So this is home, where you have some direct access to some features. You have my DOI items, which is a kind of library that where you can save designs and also data sets with the modeling. You have the catalog search, which is the door to the catalog of OMARS designs. Then you have the guided DOE, which is the way of doing design of experiments easier, because the catalog is a bit complex. So guided DOE is an easier way and is the way to do optimal design. Then you have modeling, documentation, and you probably, you don't have this, but you have a company view, I guess, but we will see that later. So for this small demonstration, we are going to click on guided DOE. So you can click as well. Hopefully we can send all the calculations together and it will work. So here we are going to specify just 4 factors, an easy one, 4 quantitative factors. Excuse me? This is if you want to calculate split plot designs. So you can also do split plot designs with the software. But we are not going to cover that today. But with split plot designs, you can calculate split plot designs for, again, different criteria at the same time, and also different configurations of the number of plot sizes and so on. So you can compare them with each other as well. So once we have just defined that 4 quantitative factors, we click on Next. Here we have a small summary where we see what we have done. We go to Optimal Design, and we have this menu where we can specify what we want. So we are going to, we have 3 options. Either you want main effects and interaction effects, or main and second order effects model. You see that when you click on one of these, the number of runs changes, because of course you need minimum number of runs to estimate such a model.
Maybe one step back. So you have 4 quantitative?
Yes.
And 1 categorical? No?
No, I didn't have 1 categorical. You can do 1 categorical if you want to. It's fine.
Don't give too many.
Well, so let's say we want to do an optimization experimental design. So is everybody following so far? Yeah?
Yeah, I'm just trying to rename my factor that I just added. This is, the name is read only or something. I don't know.
Ah. Yeah. The factors, you can go before.
Yeah, so if I want to X1, so can I give that another name?
That you can give it in the end when you download the design.
Okay.
Right now, this is how it works. If you add a categorical, you can specify the number of levels here. And afterwards, when you download the design, you can get it. Yeah. So click Next, Optimal Design, if everybody is already there. Now we will select main effects and second order effects model. We will select, number of runs that you want, maybe not too many because, it takes some time because it has to calculate them all. And the database is actually quite empty still. But I will just ask for designs between 18 and 21 runs. Here we have by default that all 3 optimality criteria are selected. By default there are just 2 random starts, so we go with default. We click Next and then click on Get Optimal Design. Then you get that message that the optimal design is... Was everything clear? Because I did it a bit fast, I know.
Do you have coordinate exchange? Do you have also other...
For design generation?
Sorry?
For design generation, you mean? Yeah, it's Fedorov coordinate exchange. Yeah. Before was point exchange with Fedorov, but in the 95, Meyers and Nachstein, they published a paper on coordinate exchange, and that has been shown to be superior. It uses Fedorov update formulas for, well, my calculation is ready. It uses the formulas for updating the matrices, so it's fast. That comes from Fedorov. Any success here? If your calculation is done, then you will get a notification. You should get something here. Yeah? Good. Yeah? You should get like a 1 here, probably. Is that so? So that means it's working. Okay. Everybody? So you click on the notification and then you will be directed to this Pareto analysis page, which is where we compare designs with each other. So I have 12 designs. Why? Because I have asked designs for 18, 19, 20, 21, number of runs, and for 3 criteria, so I get 12 designs here. I get the best designs for those criteria, right? And the design, yeah?
Did you go one step before?
Here?
No, because here I got the notifications.
In the notifications, you click on the last notification you have. And then you get to this page. Yeah, now I was going, yeah. So you have 2 parts here. You have the graphical part where you compare designs with each other, and you have the table here with the designs that they can, you can order the entries and so on. And you have some criteria here. If you click on one row, you will get the designs of that detail. Or the details of that design, sorry. Where you get summary, morphology, aliasing, with the color map and correlations. Of course, everything looks like the central composite design, powers, and so on. You can go back, and then here you have this platform where we compare designs with each other, and we have also a recommender system. So here you indicate what matters for you, like maybe the number of runs. They are optimization experiments. You may be interested in prediction, so you mark the maximum 4th order correlation, and then the G efficiency and the prediction variance. And we have a documentation site where we explain every single graph that we use here, and also the methods that are behind. But just, the graphs that we see here, when you select 2 points, then we have a scatter plot where we color the Pareto front. So we color the best designs, and you can see that is here, design number 3. If you click on Get Recommended Design, so then in this case you get design number 3. So we have a recommendation algorithm behind that, depending on the designs, on the criteria that you have selected, will recommend you a design. And if you select more, like the G efficiency, if you select 3, then you get this kind of representation, which is again a way of representing a set of items according to 3 different numerical quality attributes. And if you get more, then you get this representation. And every time you can get a recommendation, which in this case is design number 3. So if you will be convinced that design number 3 is for you, well, you can also compare designs with each other if you want. So you can select up to 5 designs and then click on side-by-side comparison and have the designs next to each other. So you can see the properties of each design just next to each other, efficiencies, powers. And here we have the powers for for the different steamable effects. So you can compare the designs with each other. You have the color map and correlations of all designs here as well. And let's say that we are convinced that design number 3 is the one for us. We can click on it. We can click on download design, continue, we'll give it a name. Then we save it. And here is where we can change, in this page, design ranges, is where we can change the name and the ranges for the factors. So once you purchase the design, because our platform is you don't pay per user, but you pay per use. So here you can specify that this is maybe the temperature, and goes from 80 to 100, and so on. And this will be taken into account when you download the design. So if you download the design, you will get this Excel file that has the design with the values that you have specified, the optimal design. Once you purchase a design, you can also download a report. So you can download the report in in Word or in Excel. So we have all the properties here, also the FTS plots, and all the properties that you see in the design detail. We have them here. And this is it for this part. So I hope everybody got their designs back, right? Their calculation was successful. You could compare them with each other, click on the recommended design. So and then select a design, see the details, and download it. So as you see, this Pareto analysis page is something that is common when you look for a design in the catalog as well. We will see that in the next block. And it's the platform that we use to compare designs with each other and make the final selection.
Is there also an option for discrete numerical? Because I saw that it was only continuous, but fully continuous?
Not at the moment. Is it something you use often?
I know for us, we always go with discrete numerical because certain settings you never have that much control over a machine or over a setting.
Right.
That you can go full continuous, so you always go with discrete continuous.
And how many values you may have?
For us, it's mostly 3 to 5 discrete.
Okay. Yeah, that should be not too difficult to implement in the algorithm, for sure. Thanks.
So and here you have a 2D graph because you selected 2 things that you'd like to optimize, and then if you hover over the point, you can see which row it is in the row, right? Which
Yes,
design is
exactly.
in the row. If you have three, you get this kind of ternary plot, this kind of graph, triangle. So how can you also hover over the points there? Because there I'm struggling to see which ones then are...
Yeah, this graph takes a bit more time to explain, of course. So the designs here are in the areas. Because let's say that this design that is here, the number 2, is the best for the power to detect interaction
okay,
effects.
So if you hover over it, it'll say the number again of the row in the table.
This is the row on the table.
Right, okay.
But this is the percentage, because
Sure.
this ternary plot is how important its criteria
Okay, so it
its
gives you
criterion
different
is.
kind of color bands, and then each color band is one design, which is...
One or several. Sometimes you have several.
Right, okay.
Yeah.
Okay. Thanks.
Okay, thank you. So we will stop. It's 3:25. So we will come back at in 10 minutes. 3:35.
Can I ask you?
Yeah, of course.
So I had some problems here.
Okay.
My account, so therefore I missed out with the account.
Which one? This?
In the beginning.
The sign up.
First step that you take. So what?
Guide.
You start. You want to guide it.
Yeah, guided DOA. Shall I go there and I? That's okay. Yeah.
So now. So I finally I had to create with another email
Okay.
address. Okay. So now you are in the guide.
Yes, this is the door to optimal design. You add the quantitative factors that you want.
Okay.
One.
So and then we just come up with something.
So just add a few more. You know, you can add 4 or 5.
You had 4. And then you...
Wait a second, because now the button is, yeah.
Okay, so...
yeah, so you add one more.
Okay.
Then you go to next.
And then next.
Yeah, next is... or you can go to summary.
Oh, to summary.
And now click on optimal design.
Optimal design.
And now there you specify the model that is interesting for you.
Okay. And now, so what did you? But you added interaction effects.
I add also the quadratics. Yeah.
So you took both.
Only one. You can, because they are nested, right?
Okay. Okay.
And then you go down in that page. No, in this one, the other.
So here.
No, the problem is that you have to. Yeah.
So,
yeah, and here you have a slider for the number of runs. Yeah, sorry.
Yeah.
So here you can specify them, because we calculate optimal designs for every number of runs.
Yeah.
Right?
Yeah.
So here, just to have it faster, you can do just don't know, 20 to 22 or 6.
Okay.
Yeah. And then next. These are the default parameters, so which optimality criteria we are considering. D, A, and I, the number of random starts. We can just go with the default.
Okay.
Click next.
Next.
And now get optimal designs.
Yeah.
Yeah, then you get this node that the calculation is being done. And now you have to wait until it's finished, and you will get a notification here. Once it is finished.
So we are waiting.
We are waiting now.
Okay. I saw that you had sent on the email.
Yeah, I sent some data sets that we will be using after.
So we will use that later on here.
Yeah.
And the presentation you have.
Is this one? Yeah, is the presentation I have. Yeah.
So is this also included in the presentation?
No, the presentation is the same presentation I am using.
Okay, as you are running.
Yes.
I see. Good.
And now, if you come back to the software, maybe it finished.
So let's see.
Yeah, it finished. You see, you have a notification.
Okay, and
then,
I press.
and then you click there on the notification, and then you get to this Pareto analysis page where we can.
Okay.
You have a table.
Yeah. So now comes Pareto analysis.
Yes. There we have the quality indicator.
Did you cross?
Maybe the number of runs you can check.
Yeah.
And the power for interactions, for example. And there you have this scatter plot with the.
Then I get a diagram.
Yes, but then you have to go down more. You go more down, maybe.
So here.
How much down you can go?
Okay.
No, because there is a table there.
Yeah, let's see. Let's see. What?
No, there should be a table there under. Can you use the scrolling like this? No. No, wait. Can I try?
Yeah, sure.
Yeah, here is the table. Yeah.
Okay. Yeah, so it was further down.
Yeah, because here you have all the designs. So there are like, I think there are like 12 designs maybe. Yeah, and then if you click on one row, then you will get the details of a design.
Okay.
So how good it is, like, you know, morphology, aliasing with the color map and correlations and so on. So you can go back. I see everything is quite big, yeah.
I thought since nowadays also other type of functions are used when modeling DOEs. But here in a way it's a polynomial
Yes.
modeling
Yes.
that we do. So that's anyway the way.
Like nonlinear.
Yeah. So you have Gaussian functions and, and a lot of different things.
Yeah, we have to choose.
But I can see that anyway. It goes a step further than I normally work with design of experiments. So
Okay.
it's interesting to see how to actually be able to interpret other things with this type of approach.
Yeah, nice.
So good, and I guess now it's time for some coffee.
Yes, go.
It's too late.
I'm going also. Okay. Bien, ¿no?
Sí. Sí, si quieren mi comentario sobre la plataforma.
Me lo das después, ahora mismo. Porque son malos, ¿o qué?
No. Tiene muchas cosas.
Tiene muchas cosas, sí.
Data coming from hospital.
Lo sé.
So, follow you when you said magician.
You like it, eh? Magician is good, eh? I think it works, right? Like kind of this analogy with professions.
Yeah, but we were still thinking what's the mathematics behind the magic. I mean,
The inverse of a function, right? Sorry.
no, I was just thinking. I mean, you have quadratic effects. We're back in the first example, huh? So you have 8 factors. So you need 3 levels here and there for some of the 8 factors.
Yes.
So now you're optimizing, so you need curvature. And the curvature in that response surface can only come from quadratics or from interaction terms. And you only have 24 parameters, and then it fits perfectly. Right? There's no error then.
Yeah, but many things there are just not
Well, but
not important.
no, but only you choose 2 or 3 quadratics, so 2 or 3 factors that have 3 levels, and those will probably always get into the model, because when those 3 responses in that one axis are a little bit different,
Not always, because
you will get something that has curvature.
in this case, in the real case, there were 5 parameters that they had quadratics, and only one got in.
So you have 5
and
3 levels.
Yeah, 5 with 3 levels and
But
3.
those are, if those are the correlated ones, then maybe you have 8 quadratics. Right? Not pure, because they're
Well,
correlated.
but the quadratic effects, they were uncorrelated in the model matrix. The quadratic effects were uncorrelated
1.5 to 2. They are probably more.
because you center them.
9 divided by 3 divided by 2.
Well,
I'm not the first one. I'm not the first one to do it. But
Yes.
no, you calculated 300 millions already, right?
I have more.
Even more.
Yeah.
Are you still continuously?
No, I just have a catalog from the university. Still time that I have to work on it, but I don't have time.
No, but I was thinking maybe having a few workstations in the backyard. That is.
Yeah, I do have, but I still have to do it.
You still have time to play piano, I hope.
Yeah. I'm playing on. Do you know I'm playing on Tuesday?
Yeah. Well, I was thinking you were playing.
Yeah.
Because I saw there's a piano recital, but they forgot to mention your name.
It is somewhere there.
In the program.
Yeah, in the program. Yeah.
In the latest version of the program.
I'm playing with Bradley Jones, who plays the violin. This is a person that was working for Jump and now is helping us. So I still have time. Yeah.
You still have exercise or what?
I still can sleep and still not a lot, but
That's not magic. I mean, that's real.
that's real. Yeah. My way. Luego vienes a la cerveza, ¿no? Y nos ponemos al día.
Mientras que después lleguen condiciones como para hacer alguna prueba de mi presentación.
¿Eh?
Mientras que después lleguen condiciones para hacer alguna prueba de la presentación.
¿Cuándo la tienes?
La tengo el martes. Todavía mañana me queda algo. Pero bueno, diría que más o menos está.
So, what do you think?
Off already, or what?
Yeah, it's like they left me alone here.
I'm alright. I thought he would be
Broke
here.
your software.
Yeah?
I broke your software.
Really? That's good.
This is my witness. I tried to create a design. It gave me error. Just an optimal design.
What do you try?
7-factor categorical and a quantitative. And it failed.
Should not be.
I don't know why.
You can replicate. You can
I don't know if I can replicate. I tried it once.
try it.
And it said,
Try it
yeah,
again.
I'm waiting. And then it came back. And it was empty. There was nothing.
Actually, we have a question. What do the random stars do actually? The designs were calculated already, right? So
No, the optimal designs, they are calculated on the fly.
okay.
So you do it 2 times, you take the best, and that is the one you compare to the.
So only the OMARS designs are pre-calculated? Or?
Yes.
Okay.
I assume that you can do more than 20 once you pay for it, or
More than?
20 random starts once you pay for it.
No, right now it's just limited to that. We thought, I mean, let's put a number.
100,000.
Yeah, but
I create designs for CNH.
we want to avoid
I'm going
people
for
doing that.
100,000.
But yeah, you're right. That if you pay, you can get it. Yeah.
So is 20 random runs enough then? Random starts?
I mean, the idea is that, well, we have checked with Jump as well in some cases, and 10 random starts was
Okay, okay.
quite often good, but we have also the database, so we are always keeping the best designs there.
Yeah,
So hopefully that will be,
in the end, that will help.
yeah, because also it becomes faster and faster, you know, which is good. If you ask for, I mean, right now all the people, they created a bunch of 4-factor designs, so now we are
Stored, indeed.
the best they get stored.
All right.
So when Robin was trying,
Yeah, I want to know about that thing.
Well, the error, the bug. Yeah. I'll try and regenerate once we start again with stuff. If I can, I'll let you know.
Yeah, if you can replicate it, just...
I'll let you know the steps if I can.
Nice. Yeah, this is good for us, you know, because software is used, but...
You get as well, the questions, UI-based questions. It's a gold mine in information, right?
Yeah. I mean, and people using it.
It looks good, by the way.
What was asked also before to change the names already when you generate? I
something
think
like that.
It
Which
was
one?
intuitive for me too. Like he asked if you can change the name of the X1 already when you
at the beginning.
I know. That's something that was before, and then we took it away. We have to think about it.
I think it's important. Users
There is a whole thing going.
or at least have a hover where they say you can change the name later. That at least they know.
Yeah.
At least give them the information if they want to change
I'm going
it.
to
If
write
it's not
that
possible
down.
technically, add it as information.
I mean, everything is possible. It's just the amount of work that's
True.
And now we
I think
are.
a hover is easy.
Yeah.
It's hotfix, let's say.
But you removed it because it was like computationally better or something to have a shorter.
No, because we changed the data schema that we were using for some things, and then was kind of a consequence of some other things.
It's technical.
And actually, yeah, exactly.
You're building up in that sense.
We're young, but we already have a bunch of technical debt. So you know how it goes.
I know.
But yeah, I think the same. Yeah, you should be able. On the other hand, yeah, many times you just want to try, right?
Yeah. Like to make it
Sorry. Yeah. And also, what happened with the first customers we had is that they didn't want to input which factors they had, you know?
Right.
Because and then we had this solution that you input it at the end, and everything happens in the client, so nothing is sent to our server.
Yeah.
Actually, nothing that you input there is sent to our server. So that was the main reason.
Actually, I have another idea. With the OMARS designs, have you looked at relaxing the constraints? Because right now you're working on they have to be fully uncorrelated. Can't you gain some on other aspects if you relax them?
For sure.
Because that's an idea for the future as well? For implementation? I'm just curious.
Enumerating designs takes an awful amount of time.
I know.
So I think right now I have still like some 500 million designs waiting to be filtered.
You need a supercompute.
And selected. No, for that not. I think we will be now just taking the best designs that appear. You know, Bradley is presenting like really nice designs for combination of 2 and 3 level factors. Then they will go thing.
Yeah, no.
I think that should be the approach now.
But I was just curious with the OMARS if you relax the constraints, because I know that if you always at the end of the constraint, if you want to reach that last bit,
you pay a price.
You pay a big price on everything else.
Yes.
Generally.
Yeah, you're true. You're right. But the OMARS is a selling thing, you know, because of orthogonality and perfect, which is never perfect.
But does it work in practice then? That's always my question. Is it worth it in practice? It's a nice selling point. It's a unique thing. But does it create that much value? I wonder. I mean, from my perspective, for Cyanation, at this point it doesn't, but I know that for Pharma it for sure can.
For Pharma it does, yeah. Because people are like happy
but even
to use.
there, is it worth the value to go for the full orthogonality?
Well, they can really be precise in Pharma. In their experiments, how they do experiments, they have a lot of experience there.
Mm-hmm. Yeah, I don't know. I'm just wondering, actually, in that sense. Because that's also why I asked about the discrete numerical. I know for us, for example, let's say if we can do 3, sometimes it's a lot. That's the accuracy at sometimes that we're playing with.
Now, discrete numerical should not be.
It's not difficult,
Too difficult.
but I think it's a value for others. I know for us, if we were to use it, it would be.
Okay. Cool. What time is it?
Nearly quarter to 7. I think we passed it by 7 minutes already. Given this.
It's normal. It was a bit intense.
Al principio me he quedado un poco loco porque mi presentación, las primeras diapositivas son casi iguales que la suya y cuando has dicho y ahora vamos a ver unos datos de un caso de granulación y el mío también es
así.
Y he dicho, wow.
Me lo ha copiado.
Es el mismo.
Bueno, no te veo. How is it? We will start.
All right, yeah.
Want to know your impressions after. Only the good ones.
So we're not
Why do men like to touch
Good. So let's continue. In this second block, we are going to see OMARS designs. I think it's just OMARS designs. And then we will couple it with a demo of the solver, yeah. So we will be seeing OMARS designs and then we will search for an OMARS design in the catalog. So the most popular three-level designs are the central composite design, the box Penken design, and the definitive screen design, I would say. So central composite design, discovered in the 50s, it is an optimization design. Of course, very much used. It has three levels. When it's face center, the axial points are centered on the face. And the quadratic terms are highly correlated, and it becomes really expensive for 6 or more factors. This is the color map on correlations of that design. So you see the high correlation between the quadratic effects. So the effects are ordered here, first linear, then two-factor interactions, then quadratic. Box Penken, also pretty old design from the 60s. Also optimization design. It solves the problem of CCD with the correlation between the quadratics, but it has a very low power for the two-factor interactions. And again, it becomes very expensive for 5 or more factors. Here we have the color map on correlations of that design, where you see it is much better for quadratics. Both designs, they have uncorrelated two-factor interaction effects as well with each other. Then the definitive screen design, much more recent design from 2011. So screening and optimization experiment at once, as we have already discussed. It has low powers for quadratic effects, so it is arguable that it is an optimization experiment in that respect. And it has a very small size, so it's normally 2 times the number of factors. The number of runs equals 2 times the number of factors. And here you see a color map on correlations of that design, where now the two-factor interactions they are correlated with each other and also with the quadratic effects. While here you only have this correlation between quadratics. So these are these type of designs for 4 factors. What do they have in common is this part here, and this is what makes these 3 types of designs OMARS designs. So OMARS is like a family that has as members central composite, face-centered, box banking, and definitive screening designs, among others. And because of this property of orthogonality. So what is that property exactly? They are orthogonal because the main effects can be estimated independently from each other. They are minimally aliased because the main effects are estimated independently from all second-order effects. And they are response surface designs because they allow the estimation of a partial or complete second-order effects. OMARS, that's the acronym. So if you were to choose a 4-factor design for your experiment, and you go to the,
Could you please go back one slide? When you were talking to Eddie a while ago, you said something like mixtures, you only care about prediction. When you were talking about the design space map with the successor probability, but then, okay, if you only care about prediction, then why is it important that these main effects are estimated independently from some other things? How does that translate into getting a better product in the end?
Because you will estimate. These are not mixture designs. So you can identify factors that they are not active, and then you can just not consider them, and that can be beneficial as well. So you can make decisions because you are able to estimate what has an effect or not.
So if the main effect is not active, you just throw out everything involving the fact that also possible interactions and quadratic effects. You just assume that they don't exist then.
That will be in the analysis, not in the design, right? So it's not in this part. So in the analysis, you will make those considerations. Either if you want a model with heredity, for example, then you will consider the main effect. Of course, if there is a 2-factor interactions highly significant, then you will include that.
Okay, thank you.
So you wanted to choose a 4-factor 3-level design. You go to the book and you find that you have just 3 options. Here is without center points, but you have the small definitive screen design with 8 factors, or the larger central composite design or box banking design with 24. If you do that for an increasing number of factors, 3 to 5, you see how these lines, the line for definitive screen design stays quite low, always twice the number of factors, but the one of the central composite design grows in a factorial way, and the one of the BBD also grows a lot. So what is the motivation of the OMARS when I was back in the university during the PhD? The motivation is to find if there are more designs with those same properties that we have described here in the middle. So designs that they will have like an intermediate number of runs between the definitive screening design and the central composite design, but they will have also the same properties. And we found that many of those existed. So there are a lot with the same properties. Here we rediscover the central composite, the definitive screening, and other 3-level designs. And what these designs they have is that they also make a kind of spectrum of the properties. When you go from the small definitive screen design to the large central composite design, then you have designs with the properties that they improve gradually from one design to the other. And here you see a table from some time ago with 309 million designs. And here you see the number of runs on the left side and the number of factors on this horizontal axis. And you see the number of designs is really huge. Every design here is non-isomorphic to the other, so you cannot build one design from the other just by permuting the columns or the rows or such, but there are a lot. So we found them using optimization techniques and high computation, so we mined them using the cluster, the Belgian cluster, the tier 1, tier 2, but also some infrastructures in the US when I was there. This is an example, a 5-factor 22-run design, where it's a fold-over design, so every row has the opposite row in the design. So, for example, here you have all the factors set to the minimum level, and the last row is all the factors set to the maximum level. It's balanced for main effects, has all OMARS, and has no center runs, but if you will add any number of center points to an OMARS design, then you still get an OMARS. Here you have another example, a curious one. This is a 4-factor 23-run design. It's a curious one because it's non-fold-over, and it is curious because the designs that are in the database of Effex, we have 200,000 OMARS, pure OMARS designs with a mix of quantitative and categorical factors, and then we have 300,000 blocked OMARS designs. The 200,000 pure OMARS designs that we have, they come from a large catalog of several hundred million designs, and they were selected. It's curious that in this huge hundreds of millions catalog that we mined, almost the majority of designs, they were fold over. The ones that they got selected to be in the catalog of OMARS, a large majority is non-fold over. So they have really nice properties, and they have been selected by themselves, and this is an example. So here, not every row, for example, this row, every factor is set to the minimum level. You will not find in the design a row where every factor is set to the maximum level. So are they any good? How to choose? Here I have 2 examples on how to choose an OMARS design. First, an optimization second-order design for 4 quantitative factors. And I consider as benchmarks reference the central composite and the box banking design. And here I have some properties for those two designs. So I have the power to detect an interaction effect, quadratic effect, the maximum 4th order correlation, G efficiency, prediction variance, and the pure error. If it allows pure error estimation, this is, does it have replicates? Are there replicates in the design? Yes.
What's a 4th order correlation?
It's the correlation between the second order effects. So in this case, the maximum. And so if we come back to the designs, is the maximum value here in this square.
Of the absolute value of the correlations?
Yes, and then you take the maximum and you use that as a criterion. So you see what we commented. So the CCD, really high power for interactions, of course, because it has a factorial or fractional factorial part. Then we have the box banking design, very low power for detecting interactions. The other way around for quadratics. Maximum 4th order correlation, much higher for the CCD, as we have seen, but the G efficiency is much lower for the BBD, so it has a much higher maximum prediction variance. And with both, you can calculate pure error because both they have replicates, so they have center points. So we go to the database and we've selected 14 4-factors OMARS designs for this scenario, so for 4 factors and with the OMARS structure. And here we have a scatter plot where we display the maximum fourth order correlation on the vertical axis and the number of runs on the horizontal axis. So we color the points in the Pareto front, which are the points, each point is a design or several designs. So the Pareto front are those designs that they have properties that they are not improved by any other design, right? For example, this design that has 22 runs, it has a low fourth order correlation and dominates this design and that design, because it has the same number of runs and it has a lower correlation, and the same. When you consider this criteria, the CCD is far away because it has a very, a very high correlation. BBD is on the Pareto front. We're going to focus on these 2 designs, which we call OMARS 1 and OMARS 2. And what you see is, is that the power for to detect interaction effects for those designs, you see that this one that is quite small, 22 runs, the powers for interaction effects is larger than the BBD, and for quadratic effects is a bit larger than the CCD. While this OMARS 2 that has 25 runs, still being smaller, it has high powers for interaction effects and also quite high powers for quadratic. So it has 2 different values for the powers. So actually this is what happens with OMARS designs. You get a balance between power for interactions and quadratics, and if you consider kind of an intermediate number of runs, you don't have to go to the CCD that is very good for interactions but bad for quadratics, or the BBD that is the other way around, so you can balance those 2 aspects. Maximum fourth order correlation is acceptable. G efficiency, you should not compare the efficiency of designs with different number of runs, actually. Prediction variance you can, so you see that it's also kind of comparable. And the pure error, the first cannot, doesn't allow the estimation of a pure error, but the second does. And I have a 2 here, so why there is a 2? Because this design, it has 2 replicates, not only 1 point, but 2 points in the design, in the factor space that they are replicated. So you get more scattered estimation of the pure error. Because
is 2 among these 25 runs? Or is
yes, 2.
Additional?
No, 2. 2 among, so there are 2 points that they are replicated at least 1 time. And this is something that we calculate for the catalog as well. So we have, for every design in the catalog, we have how many points are replicated and how many degrees of freedom do you have. So you can balance, you don't need to replicate always the center point, or you can replicate the center point and other points as well. So this is the color map of the 22-run OMARS design, and this is the color map of the 25-run OMARS design. Something curious here, this OMARS design has the same structure as the central composite design or the box-Benken design. So what I mean is that this design has a model matrix where the 2-factor interaction effects are uncorrelated, and they are also uncorrelated with the quadratic effects. And this is actually what we call strong OMARS designs. And there are a few, but they are usually quite good. Yeah, these are a strong OMARS design. So this is the one that we have seen for 4 factors, but there are a number of 5 factors and 6 factors as well. This 6-factor 40-run strong OMARS, for example, is smaller than the 6-factor CCD or BBD. So there are other options there than the classical central composite or box-Benken design if you want to do optimization with OMARS. Now the second example, yes?
So these that you showed on the right, those were all the same size for the same problem, basically.
Mm-hmm.
So they differ in, let's say, in detail. So you would really balance between some of the criteria being a little bit higher in some, and then lower for others. Is that right?
Yes. So these are designs for optimization for 6 factors with 40 runs.
So do you find a strong OMARS for every number of factors?
In the catalog, we did quite a substantial effort to go up to 40 runs. If you want 7 factor strong OMARS, you have to go higher. I don't think we have one.
Okay, but up to 6 you have.
Yes.
For every number of factors. Okay. Thank you.
Different than the central composite and the box making designs.
Yep.
Yeah. Second example is a screening experiment. So how we choose an experimental design for screening scenario. Screening, remember we have a large number of factors and a limited number of tests, so we cannot fit the full second order effects model. So we call these designs also that they are super saturated for a second order effects model. In this example, we are going to look at a problem with 6 quantitative factors where the number of runs is limited to 22. And as a benchmark designs, we are going to use the definitive screening designs with 16 to 22 runs. The projection estimation capacity of the definitive screening designs equals 3, as you know. So we have already seen what does that mean, but maybe a small recap. So this projection estimation capacity is a single number that evaluates how good that experimental design is to fit a large variety of models. If this number equals 3, which is what happens for the definitive screening designs of this size, that means that you can take any subset of 3 factors out of the 6 and you will be able to fit a full second order effects model on those 3 factors. So all the 3 2-factor interactions, 3 2-factor interactions and the 3 quadratic effects, they will be steamable. Now here we have some properties of the definitive screening designs from 16 to 22 runs. So the power to detect interaction effects is very good. The power to detect quadratic effects is not that good, something that the definitive screening designs suffer from. And the maximum 4th order correlation is also on the high side. After you have the projection estimation capacity that equals 3 for all designs, and we have this number projection information capacity, which is a bit a technicality. But our software has it as well. So what is this? This is the D efficiency. So for every projection on 3 factors out of the 6, we build the second order effects model. We calculate the D efficiency of that model matrix for that model, and we average them. So what you see here is the average D efficiency across the all 20 projection designs for a second order effects model. Is that clear? It's a measure of evaluating. So it's not only that you can fit all those different models, but it's how good you can do it.
Wouldn't I rather have a minimum there, or at least in addition looking at the minimum, because the average, if I have some models that are very strong, but 2 that are poorly.
You are totally right. You have to choose something. Literature normally is the average that is reported, but you're right. We report the minimum in powers, for example. In some other criteria, we do report, or maximum 4th order correlation, we report the maximum as well. So, okay, we look into the catalog and we find these 15 candidates OMARS designs from 16 to 22 runs for screening. And here you see another scatter plot where you have the power to detect quadratic effects on the vertical axis and the number of runs, and the Pareto front that is colored in red. And you see, for example, that this point is not red. Why? Because it's dominated by this one. Because this is a design that has 17, while this has 18 runs, and this has a higher power to detect quadratic effects. So So the DSDs, of course, they are not in the Pareto front because of the low power to detect quadratic effects. We're going to focus on these two, so one with 16 and one with 22. And here you have them, the OMARS 1 that has 16 runs, and the OMARS 2 that has 22 runs. The power to detect interactions effects is lower than the power to detect interaction effects from the same size DSD, but the power to detect quadratic effects is higher. So this is again something that we always observed. You can balance, because we have a catalog, you can balance these two powers. Actually, the color map on correlation looks very much as a DSD, and this, up to a large extent, this design is quite like the DSD. But you see that the maximum fourth order correlation is also lower than the original one, and prediction variance as well. The projection prediction variance for 3. Now let's focus on this one. 22 runs, again balance power to detect two-factor interactions and quadratic effects, lower correlation, and the projection estimation capacity equals 3.8. And this means that with this design you can fit a second order effects model on any subset of 3 factors out of the 6 and 80% of the subsets of 4 factors. So it's clearly superior than the rest in that respect, plus it has the lowest prediction variance for all the projections in 3 factors.
Question. Sorry. If you're saying 80% of the 4-factor models, is there a way for me as an end user to decide which of those I would want to be able to fit? I mean 80% means, there's a list of things, and then I would want to know which of them are. Maybe I say, well, these are of less interest to me, and those are of more interest, so I could assign factors in a way to the x1, x2, whatever I have, so to make the best out of that. But for that, I would need to know which of those are.
No, I understand. This is it's a very good question, because we had it in a consulting case where we had to carefully assign factors to columns. So it's something that you cannot do. We don't provide assistance at the moment for that. You could ask the software to give me like the best designs with that property, and then you can look at the correlations and do it. Mm-hmm. Okay, so weak points of standard designs for 3 levels. Central composite design is the non-flexibility in the number of runs. They are very expensive, high correlation between quadratics, and low power to detect quadratics as well. Box banking we have seen, again, no flexibility, you have only one option for a given number of factors. Expensive, and low power to detect interactions, definitive screening, high correlation between second order effects, low power for quadratics, and limited projection estimation capacity. Mm-hmm.
Yep, I'm wondering about the optimal designs. Would that make a good 4th column? Would that be a relevant comparison?
For screening experiments, it's not that easy to find good optimal designs. Well, first, because the full model is not steamable. The full model is not steamable, so you may need to go to what is called an alias optimal design. In those kind of designs, the two-factor interactions are going to weigh a lot, much more than the quadratics, which is actually what happened in the optimal design example that we have done. You have seen how the designs, they were looking like the CCDs, because actually the interaction effects, they weigh more on an optimal design algorithm because they are more. They are just more than the quadratics. And that balance between quadratics and interactions, I think is very difficult to get with optimal.
But
Matthias?
Can't you assign a weight then, if you do sort of weighted Would that be a fair comparison?
Yeah, I guess you could assign a weight in the optimal design generation, right? Mm-hmm.
And would that still then have the same weight that you just said, if you were to weigh?
I don't have experience in assigning weights in optimal design. I don't know how often is that done. I don't think any commercial software does that either. This is clearly a good idea, but something unexplored. Mm-hmm. Then we did some extensions. So we had this original OMARS for only numerical quantitative factors, and we extended the catalog first by adding two-level categorical factors. The orthogonality structure is preserved, and we improved previous work on mixed-level OMARS design. So there is a paper out there, also for the original OMARS. And we built, again, a large catalog. So we have, in the catalog of the software, you will see, we have also OMARS for quantitative and two-level categorical factors. This is an example that we use in the paper, I think. So we compare it with the DSD. And yeah, the usual suspect when it is related to screening experiment. So here we have a 4-factor 22-run DSD, 24 and 26. So the DSD for a combination of quantitative and categorical is not an OMARS design, because still there is correlation between the categorical factors and between the quantitative and categorical. And yeah, we saw in the paper that it's actually more advisable to use the OMARS design. This is an application, screening and optimization at once. Yeah, so another very similar application to the one you saw, where it was used such a design. The second extension is blocking. So we, yeah.
So if you, in the software, if you have a categorical factor with, say, 3 levels, you will never get an OMARS. Is that right?
So far, there are no OMARS for that scenario.
Right, okay.
So then you should go to the optimal design.
Okay.
Mm-hmm. We have blocked OMARS. So as I told you, there are 200,000 OMARS designs in the catalog right now, but there are 300,000 blocked OMARS. And why? Because we can block an OMARS design in different ways. So if you have a 24-run OMARS design, you can do 2 blocks of 12, or 12 blocks of 2, yeah, or 3 blocks of 8, 8 blocks of 3, 6 blocks of 4, 4 blocks of 6. So you have 6 possibilities. But we have tried all those blocking schemes and only have selected the designs where the block was orthogonal to the main effects. And we have at the same time minimized the aliasing between the block and the second order effects. Based on integer programming, and we built a large catalog that is also accessible through the software. And yeah, they provide solutions for novel problems, the blocked OMARS. Because if you have a screening scenario where you want to balance the interaction and quadratic effects and to optimize, to maximize the projection properties, if you have a block, there are not many options there. So you can do that with the software. So you can, well, knowing that the block is orthogonal to the main effects. This is an example. So JAMP also blocks. So this is an example from JAMP 16, where you see this definitive screening design for 4 factors, 15 runs with 3 center runs that has been blocked in 3 blocks of 5. And here you see the correlation between the blocks and the different parameters. So the blocking of JAMP is also orthogonal, so like ours. But you see that there is a high correlation here between this dummy variable for the block and some second order effects. Further, you see that the blocking scheme of jump has placed one center run on each block, right? And that within each block we also have a fold over 2 pairs, right? So this is the blocking at the Effex software of the exactly the same design. That you see that is different, it's also orthogonal, but now the block dummy variables and the second order effects, they all have the same correlation. So the maximum value here has been minimized. And you see that now you don't have that fold over structure within each block, and you have 3 center runs on the third block. So plus you have replicates, so you could assess the pure error with this design. So there are options, and we have blocked the designs with our method. This is from the paper of blocking. That there is a paper also that we published on this topic, and then you see that the powers are better and for different models, and these are the conclusions. So the catalogs offers flexibility because we have designs for a large number of runs. We have pre-calculated a lot of quality attributes of the design beforehand, so you can filter them as if you were in Amazon and made the trade-offs. Allows finding a design for novel problems like screening design blocks with high power to detect quadratic effects. And we have a multi-criteria selection approach, as you will see in the catalog. So this is the second way to get an experimental design from the software, is going to the catalog. And this is what we are going to do now. So, any question?
I got 2 questions actually. One is a very practical one. I see that you have all your correlations plotted. They look as if they are from JUMP, which I guess they are. Those, yeah.
This one.
Do you get the same or somehow also out of Effex? Because
This is not from JUMP.
This is not in JUMP?
I mean, you mean the format, or?
Yeah, just the plot, the layout.
No, the plot is ours.
Oh, it's in, okay, you would get that, and that would be before I download the design? I don't
Yes.
know what the correlation structure is.
Yes, yes. Mm-hmm.
And the other question I had is, the way to find these designs, is that a brute force, more or less a brute force approach, looking through all available designs and find those with good properties, or is there a designed way of finding those?
So it's not a brute force approach. It's based on integer programming, so discrete optimization techniques. This is actually the baggage I carried when I started the PhD. So how does it work? You build first 3-level designs, 3 columns. Then you get all of them non-isomorphic. Then you add column by column. And when you add a column, every entry of the column is a variable, integer variable. And then you build this integer programming program that actually doesn't need to visit all the parts. So it has some symmetry breaking constraints, symmetry breaking techniques there to prune parts of the tree. So you only get non-isomorphic designs. So you save a lot of time. Besides that, it takes really a lot of time. So I mean, to build the catalog took centuries of computation.
So it's a smart brute force.
Yeah, yeah.
Okay.
Mm-hmm. Smart as we could. Okay, so if there are no more questions, we will move to the software.
So the first example we did this morning, so that was actually calculating designs on the fly. That wasn't doing a lookup with a cat.
Yes, that was calculating
That's why it
designs
took
on the
some
fly.
time for it to generate.
Yes.
Okay, yep.
Mm-hmm. the way the way to look for an OMARS design is to go to catalog search. This is the most technical part of the software by far. So as I told you, it works like Amazon.com. If you want to buy a computer, you need to set the price, the number of processors you want, and all these characteristics, and then we do the same with designs because we have them, so we have calculated a lot of properties, so we can filter them. So let's look for an example with 8 3-level factors, for example. Right? So here we have the filters, right? The design filters on this side. You click on catalog search, then you go to design filters, and here we can specify how many 3-level factors and how many 2-level factors we want. If we apply filters, we will see that there are 15,437 designs coming from the catalog for 8 3-level factors, with a number of runs that goes from 16 to 46. Here you have these box plots that they indicate for different quality attributes of the design what is the distribution of these 15,000 designs. So you have the number of tests, the number of center points, you have the number of replicates, so the number of different design points that are replicated at least one time. Then you have the associated degrees of freedom for pure error, that they come from those replicates. You have the A efficiency for a main effects model, D efficiency, G efficiency, and the average prediction variance. Here, if we go further, we have the projection estimation capacity for a main effects and second order effects model. By the way, all this is explained in the documentation, so I mean there is more extensive explanation there on everything I am saying now. Here you have the projection estimation capacity that goes from 1 to 5. Here we have the maximum fourth order correlation and some powers to detect main, interaction, and quadratic effects. So we have to narrow our search, and if we narrow our search, the first thing we're going to look at is the number of runs. And in our case, we need a design that is 27 runs or less. So we are going to open the filters again. We're going to change the tab here in the drop-down menu. And instead of going for define your experiment, we are going to choose design size, power, and aliasing. If we choose that second option, we have now a range slider for the design size, and we're going to place this to 27. We can also use the number of boxes that are next to it. So the box plots, they give you a clue on how to further filter the database, right? If we apply filters, then we get 4,690 designs, right? Still a lot, but we get some less. Then we can go to graphical filtering. If you have 5,000 designs or 10,000 designs or less, you can use the graphical filter. How does that work? In the graphical filter, we use the same graph as you have seen it before. So in this graph, every line from left to right is a single experimental design, and every column is one quality attribute of that design. Here's where you can see the trade-off between the different quality attributes of a design and the design size and so on. If you would like how the design size compares to the average prediction variance, you can move it and just place it there. And then you can start placing constraints on the axis and just moving it around to see how that changes. Of course, there is an inverse relationship. The less prediction variance you want, the bigger the design should be. So if you want to get rid of a constraint, it's as easy as just clicking one time on it, and then you get back to the...
So that's what I saw how you moved the number of runs, and then you did some.
Yeah, I can, if I click and hold, and drag, I can make a constraint in this graph.
Okay, and then you say
And
only want those that are within that range.
Yeah, exactly. And then I can move it. So, and if I want to get rid of the constraint, I have just to click one time on it. So in this case, we are interested in screening. So we want a high value for this PEC. So you see that the projection estimation capacity has a value of 4 for some of these designs. So this means that some of these designs, they allow fitting a second order effects model on any subset of 4 factors out of the 8. So we can impose a constraint here. And you see that from the 4,690 designs, now we have 1,216. So any constraint that we apply here, it will be translated in this filtering value here. Further, we also want a high value for the power to detect quadratic effects, high value for detecting interaction effects, and a low fourth order correlation below 0.6. So those are criteria that you may look at if you are looking for screening experiment. And then you see that you are left with designs with 26 and 27 runs. Now you can apply graphical filters, and then you will get just those 9 designs. Was that clear? When you get less than 50 designs, you can select the designs on a table, which is next to it. And then if you select them, you can go to the Pareto analysis, which is the page you already know, and which is the page where we can make the final selection. So looking for a design in the catalog has an extra step, which is filtering the catalog and getting to less than 50 designs that you can compare with each other and make the final selection. So this part is, I would say, highly technical. We have also, we're implementing an easy way now, more guided, that you could also use the catalog. But here you have full control of every single aspect of the design. So if you select them all 9, you can go to the Pareto analysis, and then it's the same story as we did before. In the Pareto analysis, you can select number of runs, power for quadratics, then you will get all these graphs, and then you can always click on a recommended design and select it, and all the flow from here is the same as before.
What does the option corner mean? Corner is true or false?
Corner is if you have one point in the design where all factors are set either to the low or to the high level.
Okay, you get the extreme.
Yes, one extreme vertex of the.
Right.
Mm-hmm. And then, the same thing. So design 8 is recommended. You could click on it, see the details, and download the design. With your license, there is not included to download OMARS design with a trial license. So there are more things, of course, because we could do optimization, we could do blocks, but since we still have modeling and optimization, I will propose to have another break, and then to resume at 4:40. Sí, la verdad que sí. Hi, how is it going?
It's nice.
Hmm?
It's nice. Very interesting. How long can we get in it? 4 weeks. You said 1 week.
I think it's 4. It's set 2 or 4.
But
One of those.
I'm going to Malta on holidays. And this is something I'm not going to take
No?
to my holidays. Or I have to go without my wife.
No, maybe better not.
I have a question about the model that is below. It's always a linear model.
So far, yeah.
So far, yeah. So that was my question. Do you plan to extend this to non-linear model?
To Gaussian, for example. Yeah, definitely.
Go for a t-shirt.
Definitely, yeah. I mean, the modeling you are going to see is also linear. And the next thing that will be in the software that's being implemented now is mixed model. So when you have random effects.
Yes.
And definitely, another type of designs like lighting hypercube and so on.
And currently what I'm working on is standard DOE, usually study one step at once, but you have interaction between steps. And so is it something that you think about, to study multiple steps at the same time?
We have, I mean, people have used OMARS to do that.
Okay.
To do a polymerization process where you have first, you have different steps, right? Coagulation and then drying and so on. So yeah, you can use one of the OMARS as well.
Okay.
And then in the analysis, normally what becomes more tricky there is that our response in phase 1 becomes a covariate in phase 2.
Yeah, factor in phase 2.
Yeah, exactly. So you have to take that into account.
Yeah, because then it becomes like a random variable also.
A covariate? Yeah. Because it's something that you measure on the product, right? But you don't have full control on it.
Yeah, you don't have full control on it.
So
send you the email.
Okay, that's great. Thank you. That's really good. I'm very happy. You know.
I know.
Cool.
Also, I didn't receive the presentation.
No. Your email was not in this, or?
I'm registered.
Because I send the email to everybody. So.
Maybe I missed it, but yeah, I'm here. Did you send it today or?
Yeah, just right before the workshop. I will check.
Yeah, it's a space
Information, yes.
Oh my god! Yeah, I will definitely then.
Can you come just a second? Is this your email?
Yes.
Maybe it's wrong.
Yes.
Or
No, it's correct.
so maybe it went to spam or something.
Yeah, I will check.
And how is it going to be drinking then?
Oye, está Bradley por aquí, ¿lo vi?
You have all the beers that are like.
Have you seen Bradley?
I don't know.
I mean, he was there. I saw him among the public, and then he left.
Is that on?
I think so.
Okay.
Say hello.
Maybe go a little slow on the software.
Yeah.
Yeah, it's a little
faster. Yeah.
I think.
I tend to go too fast. I think because I do it so often. You know. Can you help me?
It wasn't that fast. I just think a little slower would be perfect.
Yeah. Okay. So let's try and find him.
Okay. And I noticed that there's the ENBIS meeting here.
Oh yeah.
And there's that very annoying lady, Jacqueline Asher.
We're friends.
Did you really? Okay. I don't think I can be friends with you anymore.
Friends. No, but really, it's like, she came and she always greets me. And,
okay.
But I mean, I'm a friend of you.
Yeah, we were at ENBIS 2 years ago, and
I think he left. Probably.
Annoying. Eric had a lot of questions.
Hey.
I heard you ate all cake, guys.
Where is the cake?
Where is the cake? You ate all.
Bradley left, right? Because I saw Brad, but he left.
Peter,
no?
yeah. Brad didn't eat. So they're getting some food somewhere.
Okay.
And
I
things are
thought
going
so.
well?
Yeah, so far so good. Yeah.
I will
I think.
ask for some extra.
Okay.
You open shop today?
Yes.
Hey, hi. How's it going?
Yeah, fine.
It is too far or from? No.
No, it's not too far. I'm more interested in all the details behind, so how exactly is it working, program the server. I think maybe tomorrow I might get more information, if I saw that correctly.
Tomorrow?
Not from you, but from Peter, that he might give more details on OMARS designs.
Yeah, probably.
Yeah.
He's talking about that, right?
Yeah, something.
Okay, so if you want even more, that's
yeah.
You choose, you know.
Yeah.
Okay, that's always good. when are you having your talk? You're having a talk. So,
No, I don't.
No?
No.
Oh, that's relaxed, huh?
Yeah.
Nice. I go to a conference next month that I don't have a talk.
Very good. What conference is that?
Fall Technical Conference.
Once again?
Fall Technical Conference in the US.
Okay.
So it's very nice.
Yes,
I'm really looking forward to it. Must be really nice.
Yeah. But this is like you have the workshop now and then it's done or?
No, I have a talk on Wednesday.
Okay.
What happened with it?
Weird, but
you didn't, eh?
No.
Do you want me to send it to other email? Or?
Yeah, maybe, yes.
Yeah?
You can be another.
Come with me.
Yes. I don't understand.
Yeah, it is weird, yeah. So, probably I can just forward it, right?
So need to
should be there.
Thomas again.
Maybe you can write it.
So required should be at least.
Ah,
It was
wait.
not a good one.
Yeah.
I'm not a Mac user.
I wasn't, but now I am.
Just chinging.
One or less.
That should work.
Okay.
If you make it it's more like what it doesn't tell you is greater than there should probably be some information
Yeah, it seems I didn't do anything, but she kind of got it like okay, and then say okay. She started. No, I realized this. I was concerned at some point that okay, 4 hours is really long. I won't be able to feel it, but the end is yeah.
I know. I've been doing 3-hour workshops and typically including a break. Sometimes the break was extra, sometimes not, and it's like, oh, I really have to rush to get through all the material that you could present. So yeah.
I think we really need breaks because I mean otherwise,
Absolutely. Yeah, you can't sit there for 4 hours and try to listen.
He designed this.
Yeah, it doesn't really work. No. So you were doing that for Jam before?
Sorry?
You were working for Jam, right? Or not? No.
No, I'm from PNG.
Ah, PNG. Okay.
Yeah.
Okay.
And we have, well, actually, I'm not even using Jump much. I do most of what I do in R.
Okay, cool.
But we do have a bulk of licensees in Jump, so the company overall does a lot of things in Jump. So Jump is this software.
Still like the corporate,
corporate software, and then for a broad range of people, like including.
People don't know that we have a drink afterwards. That it's not very clear, so I will add an extra slide or something to the presentation. Where are you at the moment with the slides?
I don't know.
The drinks are more important, I guess.
54.
So I will first then add a slide here. Let me do this.
You can do it. We are gonna start.
Well, but I want to announce it now so that they don't make other plans.
Todo el mundo a beber. Ah, there is coffee again. We'll take some coffee.
Quite unique.
That's live. Let's get started. Yes, thank you.
As you can see, I see that you all have a lot to share with it amongst each other. So in order to develop those conversations, we will buy you drinks at 7 p.m. and you'll be at Living Central, and we will leave after I say actually the course, and then when Peter and Brad are back, we will hand out 5 books, and if you want, you can also have some chat with them, and then we'll just leave. And for everybody that doesn't have plans yet, you're welcome to join us. Even if you have plans, you can cancel them and join us. And there will be some finger foods available as well. So yeah, cheap night out. Yay!
Leuven is a party city. But before work. So the last block, well, there is one small in the end, but now we are going to focus on modeling and optimization. So first, some theory of what is behind the modeling and optimization in the Effex software, and then some practice. Of course, general situation, you have a process or a production process that has some inputs, some controllable and uncontrollable factors, and some outputs, multiple inputs, single outputs. So at this point, we do multiple linear regression in the software, but the number of inputs can be very large. So linear regression quiz. So what is a linear regression? So everybody will agree that this is a linear regression, but what about this?
Yes.
And what about this one?
No.
Boom, there is a trick. And what about this? Yeah, this is really not. So linear regression is what we are going to do, and it looks like this, at least the ones that Effex software is focusing in, where we have a response that equals a second order effects model plus some error. In the effects model, you have an intercept, constant term, then main effects, two-factor interactions, quadratic effects. What is model selection? So we have already talked about this. Model selection is the identification and quantification of the active effects. That could be main, interaction, or quadratic effects. And here we have an example with 6 linear effects, x1 to x6. We have 15 two-factor interactions, so the product of x1, x2, and so on, and 6 quadratic effects. So the problem is which effects to choose, and there are, in this case, more than 134 million possible models. So the goals of the model selection, they may be conflicting as well. So you may be interested in estimation. So what we said, identifying which effects they matter the most, because you really want to understand your process, discover knowledge, and and identify what matters. A typical scenario in observational sciences, of course, but a second objective is prediction. So you want to predict, and you want to predict as well as possible. So you want to minimize maybe some, for small designs like the press statistic, or you want to look at other criteria. So again, there is something to balance there. The challenge, here I quote some of the challenges of model selection. Of course, identifying the most important effects to balance the estimation, prediction, quality of the models. Respect heredity or not. So this is something that has been shown that occurs in practice. I have a slide on that. Avoid multicollinearity of effects. So what you were saying, not include effects that they are highly correlated in the model, and include knowledge of subject matter experts. So maybe they also have a say in that. I have seen in some consulting cases that the subject matter experts, they were not statisticians, but they knew that certain two-factor interactions may not be there, or it didn't make sense because it was factor at the very beginning, factor at the very end, so they have some experience. They may have some experience on the sign of some effects, so factors. So this is something to take into account. Explosion of effects. This is combinatorial, of course, just a easy exponential. Of course, it increases a lot, so impossible to visit them all. Estimation and prediction, you could look at different criteria. In estimation, you could look at R square, adjusted R square, or the BIC, AICC, or AIC. Prediction, you could look at press, statistic, for example, because breaking down the sets in training and validation is not always possible, of course, with small experimental data. In heredity, there are well, these are the main types of heredity that you could have in a model. So heredity is a property of the effects that are included in a model. And there is a strong heredity, which consists that if a certain two-factor interaction is in the model, then the main effects of the factors involved in that interaction should also be in the model. And if a quadratic effect is in the model, then the main effect of that factor should also be in the model. And weak heredity is in the case of an interaction, then one of the two should be in the model. So this is the difference. And no heredity is just defined as no strong or no weak. There are some results in literature that observes that strong heredity occurs more frequently, and yeah, that there is some evidence that this is an important characteristics of the model that you should take into account. Collinearity. Yeah.
This heredity, is it also among all the design properties in the, if you do design selection in the software?
No, this is for modeling. Heredity is only when you have a model. Because in the design you assume a generic model that has heredity because it has all the terms.
Yeah, of course.
Yeah. Mm-hmm. So collinearity, often small data sets are highly correlated. This color map of a definitive screen designed for 8 factors, and you don't want to include them in the model together. So choosing a model, here we have 2 different models. Each model is a row. It's vertical. Each column is one effect that could go into the model. So we have 1, 2, 3, 4, 5, 6, and the intercept. We have 2 models here. The intercept is present in both of them, and the difference is that one has an effect here, model number 2, and the model number 1 has an effect, positive effect for this, not readable column. In this representation, the color blue indicates that an effect is negative and red positive, and here you see different quality attributes of the models. So both models, they have 5 effects. The R square is bigger for the model 1, as well the adjusted, but the AICC is better for model 2, BIC better for model 1, and they have different heredity. So how to choose? This is also a difficulty on modeling. Sometimes you have competing models from the statistical point of view.
So what does heredity really mean there? So how can you know that it's weak or strong?
In this case, you see this, you cannot really read because its definition is not so good, but this last column is an interaction between COV1 and X3. And in the model 2, you have an effect for COV1 and for X3. In model 1, you don't have COV1. That's why model 1 has weak heredity and model 2 has strong.
Sorry, is this color scheme corresponding to this regression coefficients?
Yes. Mm-hmm.
And does this p-value associated with this regression play a role here to decide whether that's included or not?
Yeah, that's a good point. In the software, we provide the same representation, but with p-values as well.
Okay,
So here the p-value is playing a role to decide whether that effect is there or not. So here, if I see a color, that means that the p-value is significant.
No, you have to check it. But we have the same representation of this graph. You will see it in the software, but with p-values as well.
Thank you.
Mm-hmm.
If some two effects are very highly correlated, would the software show you something about that?
You will see that this method selection that we implemented, the all subset selection, it takes care of it. It will never choose two effects that are highly correlated because there is another effect that improves the optimal function more. Mm-hmm. So what it is, all subset selection method is a model selection technique that loops through all possible models and selects the best according to certain criteria. Existing software is very limited because they actually do brute force approach, so they loop through every single model. And what we do is based on the work of Alan here. So we apply integer programming techniques so that we can, again, is with binary variables, so we apply, we prune the tree so we don't have to visit all the models, and we output the best models. What are the best models? Well, what we do is we set the number of effects in the model. We set which heredity we want, weak or strong or no heredity and constraint. And then we calculate the best models that they minimize the MSE, so the mean square error, or maximize the R square. And then we do that for a lot of number of effects that they could go like from 1 to 15, and for different heredity models. And those are the models that you get when you do a modeling in our software. So you don't get a single model, but several. It has a lot of potential. You can include also subject matter expert. You can leave some effects out, and you will see. And this is how you will see it in the software. So this is an example with with 9 factors. Again, the order is always linear effects, then 2-factor interactions, and then quadratic effects. You have the models. Each model is 1 row. Each column is one type of one effect. And a cell gets colored if that effect is in the model, and the color depends on the estimate. So if the estimate is negative, it's blue. If the estimate is positive, it's red. And the intensity depends on the absolute value. So this is a complex problem with a lot of different effects that could enter the model. So it is, of course, difficult to do it manually. Manually, you will get a single row. But what you get here is that some effects, they come more and more often. So there is some evidence that some effects, they are consistently with the same sign, and they are coming very often, and you succeed in identifying some quadratic effects, for example, the one of X2 here, and some interaction effects. So we have also a recommender system, similar to the one, yes?
Sorry?
No, not at all.
Is the color scheme kind of on the standardized variables, so that the higher the intensity, the more important the variable is in the model?
They are standardized, yeah. Right. The data set is normalized before analyzing. Yeah, good question. Yeah.
I have a comment.
Yes.
So regarding the correlation, one of the benefits of this raster plot is that if you see that one effect is in the model, and then in the next row the other effect is in the model, then you see this alternation that means that this
That's what I would think, yeah.
For example, here, yeah.
That's a good example.
Yeah, okay, that makes sense, yeah.
Mm-hmm.
Nice.
Yeah, thank you.
And this is now based on some whatever p-value decision saying, well, this factor is or this effect is significant or not.
The effects are chosen to minimize the MSC. There is no p-value in the algorithm to select the effects in the model.
B-squared error.
Yeah.
Oh, you're just choosing the best, whatever, 37 models with based on MSC.
Yeah.
Ah, okay.
Exactly. And from one effect to 20 or to... After we look at the p-values. Yeah. So yeah, based on literature that they... this graph, yeah, we didn't create it. We found very useful graph that appeared in literature some time ago. Then what happens when you have not one model but several? That we do the same as with the catalog. We filter it. We filter them. So you get the best models, and now you can filter them.
Question: how does the recommender system work in this case? Because you have all these different models. What is it based on?
It's based on, I think, four different criteria: adjusted R-square, AICC, a number of effects, press. It uses the utopia method. So utopia method is a way of ranking a set of items where you build an utopia item that has the best value for everything, and then you calculate the Euclidean distance of the rest of the items with that utopian item, and you choose the closest to it, after normalizing, of course. So this is the method that we use for both recommending a model and recommending a design as well. And we have, yeah, you see we like this graph very much, so we use this graph also to represent all models, and you can filter as well. You can filter the models, and you can also select effects that they should be in the model or not. So you can make the selection of the models smaller and then use the recommender system and also filter them with heredity. So, but the hard work of getting the models, of doing all this, or software does, presents you with the results, so you can just filter the models, but you don't have to do yourself this manual selection modeling. Well, that's it. That was short. So we're going to do some toy examples now with the software. I send you an email before the start of the workshop with the presentation in PDF, but also 2 data sets that we are going to use now. They are very small, but yeah, actually I see that I don't have the optimization slides. I'm sorry. Let me tell you a bit more about optimization.
They brought some new cookies and cake for whilst you're waiting. If you would want.
Okay.
Good. So I recovered the slides of the optimization. Voila. Okay, so 4 slides or so on optimization. So given the specification for each response, the goal of optimization is finding the design space. So finding this region, this hyperrectangle in the factor range, such that every combination of factor values there inside, they will output a compliant product. The challenges here are the complexity of the models, the trade-off between the different responses, finding a compromise solution, and of course the uncertainty of the model predictions. Correlation between the responses as well is an important thing that is in the roadmap. And uncertainty of the model predictions, we use confidence prediction and tolerance interval so far in the software. So how does it work? Well, we have here the different intervals for linear regression models. So confidence prediction and tolerance. The confidence intervals on the mean of the population, on a single feature observation, or on a proportion of the distribution. And how does it work? So here we have a small example. This is, Now consider a multiple linear regression model where we have a given set of factor values. So those factor values, they output a predicted response, y hat. The confidence interval y hat is like this. And the lower bound and upper bound of that response, the specifications are displayed as you see it there. Right? So what we do to calculate the probability of success, we decrease the value of alpha such that one of the extremes of the interval touches one of the specification limits. And to calculate this interval, it could be confidence, or it could be prediction, which is bigger, or tolerance, which is even larger. So we do that for each response, and we multiply them all to get the overall probability of success. Maybe with one example we can see it more clear. We have here 2 responses. So we have response 1, response 2. In this row we have the prediction surface, so the contour plot of the surface that is predicted by the model. Here we have the probability of success of each individual response calculated as we have seen. For example, this is greater than 17.4. So you see it goes from 20, 22, 24, 18. So it should be greater than 17.4. So this area should be, of course, with low probability of success because it's predicted this value, but this area is okay. And on this corner we have also values that are lower than 17 and so on. So that's why the probability of success looks like this. For this example with these specification limits, which is a maximization, it has only one interval, so only one lower bound. So what happens with response number 2? It should be minimized with an upper bound. And this is the response surface where we see that is increasing, kind of linear almost, and it should be less than 5.9, so of course it will be something like that, the probability of success, right? What is the probability of success of both being within the specs is the multiplication, so it becomes this one. So in this graph, yeah, you see it, the contour plot for two factors, right? Don't know if there is this clear? And then to calculate the probability of success, you could use confidence, prediction, or tolerance intervals. Where in tolerance intervals, the coverage has been fixed to 95.
So I think I didn't get how you combine them actually. Do you multiply them, or okay, that means if that's how it looks like. If you with 2 it still works okay, but if I had 20 responses, I could have one which is completely out of its range, but all the others are great, so it would give a high confidence or a high probability. So you would be happy with that. It would be flagged in yellow here.
But maybe you have a limiting one, you mean, right?
Well, if you have, I mean, it looks like if you take the I need to think about that again. I'll do that after the break.
Perfect. Yeah, so the multiplication, of course, yeah, here is 0, so here it will be 0 too. Yeah, here you will get these parts, right? So you have these parts, and so on. So we use a frequentist approach. It works well, it's very responsive, as you will see. So changing the specifications and calculating the graphs is going pretty fast. With a large number of responses, so I have solved problems with a lot of responses, and it works well. The correlations between the responses are not taken into account in the current solution that we provide. That will be nice to have. Also, Bayesian optimization will be really nice to assess the sensitivity of each candidate of optimal setting. So this is something clearly to think about. And yeah, we are also working on an analytical optimization as well, so we can guide that process a little bit more. But we have seen that the tools that you are going to use, they have been used by engineers with no statistical training, and they are happy discovering how the process works by just moving the axis of a graph, not knowing too much, I mean, where the models they come from, but just exploring the data. So
you said correlation among the responses are not taken into account. Why?
Because we do at this moment multiple linear regression with a single response, so we don't do multivariate that will take that into account.
Is it something that you plan to do?
Yeah, definitely. Sometimes you have several responses that they measure the same phenomenon, right? And they are naturally correlated. So now, yes. Now we can go to the software. So I send you 2 documents, 2 data files, both in Excel and CSV format. So let's open the one that is called tire thread.
Do you open it from within the software?
No, you have to open it with Excel or any other program that you have for numbers.
Right.
So how does it work? You go to modeling. Well, by the way, this may be important. So once you select designs in the catalog, they appear here. If you want to clear selection, you can clear selection as well. You may have that too. But coming back to the modeling, so you click on modeling, you go back to your data set, you will select it, you copy, we come back to Effex, we click here where the sign is, just we click one time, and now we do Control V. Magic? Magic, it's magic. Yes?
Would you import into that? Because we don't provide it.
What is it?
You really don't like copying and pasting by users?
You don't like copying and paste? No? Okay, okay. Yeah, certainly we can do that, yeah. I understand.
But you can drag the whole.
Not at the moment, no, because we don't have a way to distinguish also the tabs and so. Yeah, right now we chose for copy paste. But it's good to know. Yeah. Thanks. Everybody got the data set in the software? So the next step is to give it a name. So give the name you want. Tires. A description if you want, but the name is the one that needs to be filled in. When you copy paste, you can select if it has headers or not. The next action we have to take is to label the columns. So by default, the last column is labeled as a response, but in this case there are two responses, so abrasion is also a response. So we are going to label abrasion as a response as well. The software is smart enough to detect if a column is quantitative or categorical. So for now, everything is quantitative, and that's fine. So we can save the data set, and then we go to the next step, where we will define the modeling parameters for each one of the responses. If everything is following, everybody is following, and okay. So how does it work? We select the first response, abrasion, and we specify the model definition. So what is the maximum model? What are the effects that we want to consider for this data set? We want to consider only main effects, or main effects and interactions, or all the full second order effects. We click on the last one, and yeah, in this data set, everything is positive. So you can also study different transformations of the response. So you can also, let's say that I also want to look at the log transformation for this response. Then we activate the second response, elong, and we do select again the main effects and second order effects as model definition. We're good to go. So let's click launch modeling, and then we should get message that things they have started, and you will get a notification when they have finished.
Initially, the software recognizes aberration as a factor and
So that is in the. So when you copy paste, yeah, recognizes as a factor, but you can click on response. Yeah.
Okay, thank you. So just to add on the discussion that was just on uploading files, copy paste also has a difficulty in the experience that if you're on a different local and you've got a comma as a decimal point,
Yes.
so it just doesn't work. So you would have to change that in Excel first and then copy it. So
I have that problem.
Yeah.
I had that too.
Okay.
In our location in Sweden, like half the users have decimal points and half the others have commas.
Yeah, it's
and
same.
nobody can figure out
Same.
why.
Similar for
It's amazing, yeah. So there is no uniformity there. It's
I think it will be different for me in Excel versus Java.
So probably change it. I think it's in the Windows regional settings.
Yeah.
You can change it somewhere, yes. But then, I mean, you start copy pasting, or you have to do that.
yeah, true. Every time you're in the software, we have this feedback button that we will be really grateful if you can test it and send your feedback. So you can draw on the screen or give a general feedback on the page. So if you say,
Like for this, you can easily say that it's impossible to copy paste, and then we will.
yeah, exactly. So you can click next and leave the comment, and that will come to us. So this will be really useful. So is the feedback capability clear?
No.
So in every screen we have this small tab
Yes.
where you can give feedback on the general page or on a particular part of the page.
Mine is still in progress.
Eh?
Mine has been calculating for 1 or 2 minutes, I think.
Really? This should be much faster. Can you?
So how do I get this data set modeling info?
Yeah, if you go to my DOI items.
Okay.
Now you can go to my DOI items and you have saved the data set. So here you have the designs that you have saved, but also the data sets.
Okay,
so here you can click on the data set that you have sent for calculation. Yeah.
Yes, but we're collecting all.
And probably is it finished for you, the calculation? Has it finished? Okay.
So this model task, I think it's one of probably not how you start an analysis. So you start using a histogram, and for example, for the transformation, I usually go back to transformations after I completed the model and realize that the results are not good. So is there a way to, or is in the works to have some simple box plots, histograms of the columns?
Yeah, descriptive analytics, that's something that we want to add. But actually, we focus on the things that they were making us special, which is the modeling section, assuming that the people will have other means to draw a box plot or a histogram. But you're completely right. I mean, it's something that is it needs to be assessed also to decide. But yeah, we gave priority to the modeling.
Yeah, because if I have to run a histogram, then at that moment I have to think about alternative software to do it.
You can do it in Excel, and everybody has Excel, we assume. It's similar to the decision we made with the dataset, that we assume that the dataset is cleaned. So we don't provide tools for altering a table, right? Like editing and changing columns, and so we assume the data is cleaned once it comes to the software. But yeah, the descriptive analytics is something important, yes. Everybody got the dataset analyzed? Hopefully? Yeah?
Can I then select one model? I see a button.
Okay, you are already there. So you select models, right? Here in this graph you see there are 26 models. You can see them here. You can change the response here. You can change the transformation here. You can see the coefficients, or you can see the p-values. So if you click here, you see the p-values. You have several ways of filtering this, this set of models. First, visualization changes. The intercept is not conveying so much information, so you can take it out of the picture. So if you click here, you don't show the intercept, because very often the intercept has a much higher value than the rest, so it also biases the other effects. So you see it's 135 here, and this is 26. So if we click on this toggle button, we don't show the intercept, we show the effects. You can, instead of seeing the coefficients, here you see the estimates. You can see the p-values. So the p-values are coded from 0 to 0.5, no, 0 to 0.1, 0.1 to 0.5, to 0.10, and so it has a color code. And you see that in this case, yeah, all this quite significant here. You can see the p-value and the model number and the effect if you place your mouse on any cell of the heat map.
Are these models sorted by MSE? So the top one is...
No, I think right now they are sorted by size.
By size, okay.
Yeah, we didn't implement any sorting.
Yeah, and I was just wondering whether the best model had effect, if it were the top one, had an effect in it that comes with a p-value of more than 20%. That's more.
This one, yeah.
That's uncommon. But is that not the best model actually, and it only shows up in one or two models and not the rest? Then probably you didn't take that factor into account.
Yeah, exactly.
But yeah, I was wondering whether that was sorted. If it were sorted, then it would be.
No, it's sorted by size, and probably this effect came into the model because the model was forced to have so many effects.
Okay.
Then, so you can filter this set of effects by removing the effects with weak heredity and only having the strong heredity. So you see that we have now 24. You can also, as you say, don't give me models where that quadratic effect of sulfur is there. So you can also get them out. And you see that now suddenly that column is completely blank. So we can also, visualization-wise, not show that column. And the last thing I want to show you is the graphical filtering. The graphical filtering is what I saw before. It's a parallel coordinate plot where we have all the models and where we can select them. So we can select models with a low press and a low Akaike information criteria, the corrected. And then we can filter the set of models. If you click OK, we see that we have just 6 models here. And in any selection that we make, we can always use the get recommended model. And the get recommended model will give you model details of that model, where you have all the effect details, where you see everything is highly significant in this case. And you have the residual plots as well. So you get all the information of the model, and you can select the model to bring it to optimization. So if you select the model, you come back to this container page of the dataset, where you can see that for aberration, a model has been selected. So we can do the same for Elon. So we can come back to the models and go to Elon, and probably just fast this time, just select slow press, click on OK. We go with the recommended model. We select the model as well, and then you can see in this container page for the dataset that for both responses a model has been selected. When you selected one model or more, you can bring them to optimization just by clicking here, and then you can start the optimization part of the software. So far, so good. It is incredibly late. It's like 5:35, so
If you have a blocking variable, how do you specify that it is a blocking variable?
This is something that is in the making, so the next release will have mixed model, and you identify that when you do the labeling of the columns.
Right.
So when I select the first model, then I want to select the second one, the collaboration. But I'm not sure I did it right, because there is the option deselect model, so that means...
That means that you have selected a model there already.
Already? Okay.
Uh-huh.
So I have to go back to the model.
Yeah, and then you have to change the response here. Like you go to select models and you change here the response. Shall I go there?
So I tried to go back to modeling, but then...
Yeah, but this is to start a modeling. Maybe you can go to my DOI items, data sets. Then you click there. Then you see you have selected a model for aberration. Now go to select models. And now select another response here.
That's why. Okay. I forget to do that.
Yes. Yeah?
Okay, so then
Empty.
So then maybe it wasn't completed, but here it says finished.
So once you have selected one or different models, you can bring them to optimization just by clicking here, and then this button will activate the start optimization. Now if you click here, you go to the optimization platform, where you can input the specification limits, and then you have the parallel coordinate plot, and you still don't have the profilers, because this is something that we're gonna release soon, but we also have prediction profilers. So what we are gonna do, we're going to minimize the aberration by setting an upper bound of 150 and set the specifications for that response to be minimized. And we are going to place the E-long on target between 300 and 500. Now this gets carried by the next step. So the calculations here in the parallel coordinate plot take that into account. So you see the 3 different factors here, the 2 responses, and the probability of success of being within specs. Of course, this is very low. We are only considering 2 levels for each factor, so the low and the upper level. But we can increase the discretization, so we can consider 3. And now you see that probability of success improves because we have considered more points in the factor space, but we can even arrive to 11 points. And then that allows us to, to explore the factor space. Now this graph is very dynamic because you see that the silica goes from 0.38 to 2.01, and you may be interested in seeing what is happening in this central part. The same for the second factor. You may be interested in what is happening between 50 and 45. So when you make such constraints, you can click on zoom, and then the graph will be recalculated, but only considering those intervals that you have set. There is an accompanying table that contains the best points according to the probability of success. With any filtering that you make here, the table gets updated. And what else? Yeah, we have also, you can define factor values. So if you would like to see what's happening when this is fixed to this value, you can fix it, and then this will be taken into account for also plotting the graph. You can change the interval type for prediction or tolerance, and then you see how this affects as well the graph. And you can reset selection and come back to the original state, and also unfix this so we come back to the original. What's next? Next is profilers. So profilers are there already, so they will be available very soon. This is more like the standard prediction profilers that you find in other software for the different responses. With the particularity that we also have profilers for probability of success, where you can assess what you were saying, that some responses may be more limited than others. So this is something you can see in this graph, because you will have a probability of success for every response, a profiler, but also an overall. Any question? It is too late, probably. Has been a long afternoon.
That's yeah, would you be able to get a model? Yeah, I suppose I would want to play it in my own favorite software. See the regression model myself. So, okay.
Yes.
Would you go back? Yeah, you would need to know the terms that it's selected, I suppose.
Yes, you go back. So if you go to the container page of the dataset, which is in my DOE items, datasets, you click on the dataset. Here you see that you have selected models for both responses. If you click here on this cube, you will get the model details for that response. And here you have the effect details where you see the coefficient, standard error. So there you have all the information. Mm-hmm. The optimization ends the technical part of this workshop. What is left is a few words on the platform itself, because it has some particularities as well. I'm going to show you just one of them, and maybe our CEO, then we can finish the workshop. So let me show you what is behind this company view button here. So if you click here, and each one of you has a company right now. I think the trial license is made in such a way that you have a company, which is yourself. But how it works is that you can invite people. This was something requested by current customers because they wanted to have several roles there. They wanted to have an admin that was able to purchase designs and then users. So this is something that you can do with the software. And normally this is how it's being implemented at companies where there are a few admins and then a big number of users. Advantage of having a web-based application is that designs, they are shared. Modeling and analysis, they are shared within a company. So really, you can work on the same project, and different stakeholders, they can look at the same data. So thank you for my part. Really grateful to have you here. I mean, it has been an experience for me as well. And yeah, there we.
I think it went rather well. So before we continue, I think the most important part is that we have 5 books to hand out to you. So, because it's a shifting question, so you cannot, I have to make sure that you're not, let's say, cheating. So, you get a piece of paper, and I give you a question, and you have to write down the answer on the paper, and then Jose will just fetch it, and then and you have to put your name on it, else it's impossible to, to see it. And then, the 5 with the most close answer, they get the book. So the question is, how well did you listen during the course?
Nice.
You should tell us beforehand.
That's cheating. But you already have a book, so.
Well, some people have worked on OMARS, so like that.
Cool.
So the question is, when we have OMARS designs with 6 factors and 30 responses, how many OMARS designs do we have?
30 runs. What?
30 runs, that's it.
6 factors, 30 runs.
Yes, so Jose showed like a slide with all, it's just, I know you cannot have it, so you just have to ask them.
They have the presentation, so you should not look at the presentation.
Just have to guess.
That's forbidden.
So indeed, you have 6 factors, 6 and 30 runs.
How many non-isomorphic OMARs were presented?
30 runs. So how many OMARS designs do we have for that specific situation?
Good one.
Uh-huh.
You know it, no?
Of course I know the number, but I can't tell. So just write something down. I'm going to collect the answers.
That number is probably still growing, right?
Yeah.
The ones on the table, I guess. Yeah.
So and then.
So do you write a number?
I did write the number down. There you go.
Okay. Thank you. Thank you. Hola. Okay. Okay.
Thank you, thank you. So you have all the, so Jose is going to check and see for the file and source it. So for me, I just wanted to have indeed about the platform features. Jose already explained that how you can, so if you indeed have a company, and so the part of the software is actually that we do not have a user-based software, but actually usage-based. The reason we chose for this approach is that in the customer conversations that we have so far, every time we have the same discussion manually, that you have
Did you know that I invented the correlation subplot?
cadence in a design of experiments.
You are in the correlation
you search for a design,
I invented the correlation
and then you
subplot.
actually do the data
The
analysis.
color map.
But in the timing that you do the experiment, depending on what kind of
Okay, no,
experiment
I didn't know
it is,
about the profilers.
you have a long period of time that your software is basically collecting dust. And talking to procurement, they don't like that kind of idea that there's a statistician A and then a statistician B, and they all do these experiments and they all have this need for this software, but they use it in total different timings, and so a lot of the time the software is just standing. And so the usage-based software actually kind of elevates that problem, because in the end you can enroll as many people as you want on the platform, everybody can search for a design as much as they want, you can look into the designs that you have already purchased, they're there for everybody. Also the analytics and everything is available, but you do not have to, buy the software per person, you just purchase the design and the calculation when you need it. So that's how it is. And we also have, of course, a management system in there, so that not everybody can just like start downloading and stuff like that.
6.
Credits, because we know, of course, that this is something that companies do not like either. You still want to be able to kind of control it, but even for that, we have an easy flow to take it. And then the other thing is as well, it's a SaaS software, so that means that in the end, the most important thing you have is Wi-Fi connection. So that means in the end, whether you have an Apple or a Windows computer, it should not matter. Also, you do not need like a very heavy calculation machine. So especially for companies that, I know it's less of a European problem or an American problem, but more like Asian and Indian, where there are like different kind of, powerful computers. And so we do not need it with Effex. The heavy calculations is done on our servers, so that is easy also.
Can I ask a quick question? When you said you purchase a design, do you also purchase the analysis for that design, or how you deal with the modeling part?
We actually separate it's again calculation time, and it's basically more expensive the heavier the calculation. So that's how it's divided. We have designs. We have analyses that are so small that it's basically done in a minute. So for that you do not actually take credits. It's just only when you have the really heavy calculations that it goes up. So that's
and one word for that, like the analysis you made today, that's for free because it's quite fast. Optimization is also, included in the platform fee, because optimization actually is happening. Sorry, Anne. With your computer, so the calculations are done at the client.
Okay, so you pay dependent on
the amount of input factors and the amount of responses that we actually have and are happy we have.
And do you know that upfront, how much you will be charged, or is it kind of?
Yeah, no, we're actually making a very easy, chart where it's very easy for you to see, like, okay, if we do that, then it's that, then you can, or that you can know beforehand what it will be. So no surprises with regards to that.
Sorry. Can you tie this into your SSO system? Can you tie this into our single sign-on system?
We have not done that, but I have already had that question already by other companies as well, and it's something that is, up to the development team to take it on when you say like, okay, we have probably not Microsoft Authenticator. Yeah. So yeah, we have already checked into that and have already talked to Microsoft to be able to integrate that system. Yes. These are customers that have already worked with the software, either worked with designs of the OMARS designs, used the Jose and Peter as consultants in the past to help them with specific questions for which they used OMARS designs. So we have already a lot of customer validation, and cool part is that Bernard Frank is here as well from GSK, and they did with the Sartorius machine, they used the OMARS design to do a specific vaccination experiment. And so you can definitely ask him about it, because they also have done already some presentations on different conferences. And then next month, no, actually this month still, Sanofi, Marion, will have a presentation with Jose as well about what they did with the OMARS designs and with the Effex software. So also with regards to that, definitely check out also with Jose and Peter as well for the W. Al Gore case, because those are cases that are written out and that for which we also have results that we can share with you. For other ones, it's more private stuff. So, and then about Effex, I just wanted to share this really cool picture with you of Jose's PhD, but we're incorporated in June 2023. But before that, there was a long period at the university, so for the ones who are searching Jose, here it is. And I think, Seth, this is you, right? Yeah. Yeah.
It was Seth. Yeah.
And then, so indeed we have a long period at the university. So with regards to that, already a lot of research and a lot of trials, and then indeed the customer validation. So, and this was the first board meeting, and the last year was basically this, going everywhere and trying to spread the word. And I also wanted to share with you the team. So this is the Effex team with me and Jose, and then the developers, and also Tom and Seth already put you on there as well, and then Peter and Bart who are helping us on the side with our scientific advisories. So that was it. So thank you so much for staying with us for exactly 4 hours, which is really cool. So now we're going to release you. You can. We will also say who won the books. We can have indeed Bradley Jones here with us, who is actually helping us with the software. So Bradley Jones is helping Jose a lot with testing the software, also looking into the algorithms for the designs and stuff like that. So we're very grateful that he is here today with us and that he's in Leuven. So do take the opportunity to also talk to him, and then afterwards we'll go for drinks. So who's joining, by the way, for drinks? Okay, cool. Nice. So then we'll all
You should check the number.
Can you give me the number? I don't know it by heart. Yeah, I forgot. But I ordered them, so.
60,000.
No, it's a different one.
It's a different one? Okay, wait.
That's one.
Here, so pick 6, and here. This is
27 million.
That was, I have said
27 million.
6,
So, Sergio, congratulations. You said 109 million. So you.
Yeah. So he already wins or not?
Yeah. Yes.
Okay.
So next is Thomas with 12 million.
Okay.
Then we have. Anyone that
Somebody who
claims
should
this
have,
as.
Congratulations.
With 5 million. Then we have Joris with 1.6 million.
Okay.
And Matthias with also 1.5 million. Congratulations.
Congratulations. It's a unique excellent.
Nice.
La verdad es que lo quería.
Sí, oh, perfecto. Pues fuiste el que más te pasaste, pero bueno.
Árbitro entonces.
Okay, I will take it on the recording. Yes, no problem. And I will, yeah, and I will let you know. Can I have your email address? So I will send you an email.
Yeah, but you might not remember. Well, you might remember my email, but I didn't have my